Maxwell's demon with zero energy. Imagine a box divided into two chambers with a tiny door between them. Both chambers contain gas molecules moving at various speeds. Now picture a microscopic gatekeeper, Maxwell's demon, observing each molecule and selectively opening the door to let fast molecules pass into one chamber and slow molecules into the other. Without expending any energy of its own, this demon appears to sort the molecules, creating a temperature difference between the chambers. Hot molecules accumulate on one side, cold on the other, seemingly violating the second law of thermodynamics by decreasing entropy without energy expenditure. This thought experiment was proposed by James Clerk Maxwell in 1867, creating one of physics' most enduring paradoxes. The second law states that the total entropy of an isolated system always increases over time. Disorder naturally grows, never diminishes. Yet Maxwell's demon appears to reverse this fundamental principle without any work being done. For nearly a century, physicists struggled with this paradox. The turning point came in 1929 when Leo Szilard connected the demon's activities to information processing. Szilard realized that the demon must gather information about each molecule's speed and position before deciding whether to open the door. This information acquisition and processing, he argued, must have an energy cost. The paradox lingered until 1961, when Rolf Landauer at IBM made a breakthrough discovery: erasing information requires a minimum energy expenditure of kT/2 per bit, where K is Boltzmann's constant and T is temperature. This became known as Landauer's principle, a fundamental connection between information theory and thermodynamics. But there was still a puzzle. While Landauer showed that erasing information costs energy, acquiring information doesn't necessarily require energy expenditure. Could the demon operate without erasing information, thereby circumventing this energy cost? Charles Bennett addressed this question in 1982. He demonstrated that while the demon could theoretically acquire information without energy cost, its memory would eventually fill up. To continue functioning, the demon must erase old information, incurring Landauer's energy cost. This energy expenditure is precisely enough to ensure the second law remains unviolated when considering the entire system, demon plus gas chambers. The debate took another turn when researchers considered quantum mechanics. In the quantum realm, measurement itself affects the system being measured. The observer effect. Quantum observation requires interaction, which necessarily involves energy transfer. Some physicists argued this quantum energy cost would prevent a zero-energy demon from even acquiring information in the first place. Recent experimental work has brought Maxwell's thought experiment into reality. In 2010, researchers at Chuo University in Japan created a working version of Maxwell's demon using a single electron. They confirmed that information processing indeed requires energy, validating Landauer's principle. Similar experiments at Simon Fraser University used light to sort molecules, finding that the energy cost of information processing precisely matched theoretical predictions. The question becomes even more fascinating when we consider the thermodynamics of computation at the limit of physical laws. Modern computers generate heat primarily because they operate far from thermodynamic efficiency. Theoretically, reversible computing could approach zero energy dissipation for computation itself, but memory erasure would still incur Landauer's minimum energy cost. Some physicists have explored potential loopholes. What if the demon used quantum superposition to store information without erasure? Could quantum entanglement enable information processing without classical energy costs? These approaches face their own challenges. quantum systems must eventually collapse. When measurements are made, and maintaining quantum coherence requires careful isolation from environmental decoherence. In 2019, researchers at the University of Oxford proposed that a quantum daemon might exploit contextuality, a quantum resource that allows measurement outcomes to depend on what other measurements are performed, to potentially operate below Landauer's limit. However, when accounting for the full thermodynamic cycle, these approaches still appear to respect the second law. There's also the intriguing connection to black hole thermodynamics. According to Jacob Bekenstein and Stephen Hawking, black holes possess entropy proportional to their surface area. If information falling into black holes is truly destroyed, this might represent an ultimate form of information erasure, with corresponding thermodynamic costs that preserve the second law even in these extreme environments. The quest for a zero-energy Maxwell's daemon continues to inspire research at the intersection of information theory, quantum mechanics, and thermodynamics. It has profound implications for the fundamental limits of computation, the nature of information itself, and whether the laws of thermodynamics are truly inviolable. What makes this problem so captivating is that it reveals deep connections between seemingly disparate areas of physics. Information isn't just an abstract concept. It's physical, with concrete thermodynamic consequences. Memory, measurement, and computation aren't just mathematical processes. They're physical operations bound by the same laws that govern matter and energy. So can Maxwell's daemon operate without expending energy? Our current understanding suggests no. The daemon must eventually pay the thermodynamic price for information processing. The second law appears safe, not just as a practical limitation, but as a fundamental boundary woven into the fabric of information and physics itself. Yet the search for loopholes continues, driving us toward a deeper understanding of the profound relationship between information, energy, and the arrow of time that defines our universe. Cosmic expansion inside a black hole. Picture this: the ultimate collision of two of modern physics' most profound concepts. The relentless cosmic expansion driving our universe apart, and the uncompromising gravitational singularity of a black hole where nothing escapes. Tonight we explore a fascinating question at the frontier of theoretical physics. Can space itself expand within a black hole's event horizon? To tackle this mind-bending problem, we must first understand two seemingly contradictory phenomena. On one side, we have cosmic expansion, the observation that space itself is stretching, carrying galaxies away from each other like dots on an inflating balloon. This expansion, described by Einstein's field equations and confirmed by Edwin Hubble's observations, operates on the largest cosmic scales. On the other side stands the black hole, an object whose gravity is so intense that beyond its event horizon, nothing, not even light, can escape. Inside this boundary, conventional understanding suggests space is inexorably contracting toward the central singularity, not expanding. The conventional wisdom states that inside a black hole, the radial dimension essentially switches roles with time. What was once a spatial direction becomes temporal, forcing all paths to lead inward to the singularity, just as time in our normal experience always moves forward. This mandated inward motion seems fundamentally at odds with any notion of expansion. However, recent theoretical work has revealed surprising possibilities. In 2010, physicists led by Nikodem Poplawski at Indiana University proposed that black holes might contain entire universes. Their mathematical models suggested that the tremendous densities inside a black hole could trigger a process called bouncing cosmology, where collapse transitions to expansion through quantum effects. General relativity itself doesn't necessarily forbid expansion within a black hole. The mathematics tells us that space can have different behaviors in different directions, while matter must move inward along the radial dimension inside a black hole. Perpendicular directions could theoretically expand. This would create a bizarre scenario where space compresses in one dimension while stretching in others, like squeezing a balloon in your hands while it continues inflating. This raises an intriguing possibility explored by physicists like Lee Smolin in his theory of cosmological natural selection. Smolin proposes that black holes might give birth to new universes with slightly different physical constants, establishing an evolutionary process for universes themselves. If true, our own universe might be inside a black hole in a parent universe, with our cosmic expansion occurring within someone else's event horizon. Russian physicist Vyacheslav Dokachev took this concept further. In 2011, he published calculations suggesting that stable orbits could exist deep inside certain rotating black holes. In these regions, space and time would behave differently than near the event horizon, potentially allowing for expanding space and even habitable zones within these cosmic leviathans. But there's a critical complication. The interior of a black hole isn't just curved space, it's dynamic. The Raychaudhuri equation, a key result in general relativity, tells us that gravity's tidal forces tend to cause congruences of geodesics to converge. In plain language, gravity pulls things together, working against expansion. Inside a black hole, where gravity reaches its most extreme, this convergence effect is maximized. Quantum effects complicate things further. Near the center of a black hole, we enter the realm where quantum gravity should dominate. But we lack a complete theory of quantum gravity. Various approaches like string theory and loop quantum gravity make different predictions about what happens in this extreme regime. Some models, like those developed by theoretical physicist Carlo Rovelli, suggest that quantum effects prevent the formation of a true singularity, instead creating a bounce that could connect to another expanding region of spacetime. This quantum bounce could manifest as a form of expansion within the black hole's interior. Recent research has also explored connections to dark energy, the mysterious force accelerating our universe's expansion. In 2019, Kevin Croker and Joel Weiner published work suggesting that the mass-energy contribution of collapsed objects like black holes might be misunderstood in our cosmological models. If black holes contain expanding spacetime, it could potentially connect to the dark energy problem. The holographic principle adds another layer of complexity. Developed by Gerard Hooft and Leonard Susskind, this principle suggests that all the information contained within a volume of space can be represented on its boundary. Applied to black holes, this raises profound questions about whether the interior volume is real, in the same sense as exterior space, or whether it's an emergent phenomenon encoded on the event horizon itself. From a mathematical perspective, Joan Maldacina's ADS-CFT correspondence, a special application of holography, reveals that what looks like gravity in a higher, dimensional space can be equivalent to a quantum field theory without gravity in a lower dimensional space. This duality suggests that expansion inside a black hole might be reinterpreted as a purely quantum phenomenon on its boundary. Einstein's equations permit solutions where black holes connect to expanding universes. These are the famous Einstein-Rosen bridges, or wormholes. While classical wormholes are non-traversable and unstable, They demonstrate that the mathematics of general relativity can accommodate connections between black hole interiors and expanding spacetimes. What makes this question so profound is that it highlights the incomplete marriage between quantum mechanics and general relativity. In the extreme conditions inside a black hole, both theories must somehow reconcile, and the nature of space itself, whether it can expand or only contract, becomes a critical test case for any comprehensive theory of quantum gravity. So, can space expand within a black hole's event horizon? Our current understanding suggests a fascinating, if incomplete, answer. Classical general relativity largely points to no along the radial direction, but possibly in perpendicular directions. Quantum effects might enable expansion through bounce mechanisms, and holographic principles raise deeper questions about whether the interior volume exists in the way we intuitively think. This impossible problem reminds us that at the frontiers of physics, where black holes meet cosmology, our most cherished theories reach their limits, pointing toward new physics still waiting to be discovered in the mysterious darkness beyond the event horizon. Quantum superposition of a macroscopic object. In the subatomic world, particles routinely exist in multiple states simultaneously, a phenomenon known as quantum superposition. An electron can spin both up and down. A photon can take multiple paths, existing in a ghostly limbo of possibilities until measurement collapses this quantum fog into a single reality. But could something as massive as an entire planet, with its quintillions upon quintillions of particles, ever exist in such a superposition state? The question stretches our understanding of quantum mechanics to its breaking point and forces us to confront the mysterious boundary between the quantum and classical worlds. When Erwin Schrödinger conceived his famous cat thought experiment in 1935, he intended to highlight the absurdity of applying quantum principles to macroscopic objects. The idea that a cat could be simultaneously alive and dead seemed preposterous. Yet quantum theory offered no inherent size limitation. This paradox remains at the heart of the quantum measurement problems. Why don't we observe large objects in superposition states? The most widely accepted explanation comes from decoherence theory, developed by physicists like H. Dieter Zeh and Wojciech Zurek in the 1970s and 1980s. Decoherence occurs when a quantum system interacts with its environment, causing the delicate phase relationships that enable superposition to rapidly disperse into the surrounding world. The more particles involved, the faster decoherence occurs. For a planet with approximately 10 to the power of 50 atoms, the timescale for decoherence would be unimaginably short, far shorter than any conceivable measurement time. But decoherence doesn't solve the measurement problem completely. It merely explains why superpositions become practically unobservable for large objects. Theoretically, quantum mechanics still permits planetary superpositions. They're just extraordinarily fragile. Experimental evidence for macroscopic quantum behavior has advanced remarkably in recent decades. In 1999, researchers demonstrated quantum interference with Buckminster-Fullerene molecules, which are carbon structures containing 60 atoms. By 2019, scientists at the University of Vienna achieved quantum interference with molecules exceeding 2,000 atoms, with masses over 5,000 atomic mass units. These experiments show that the quantum classical boundary extends further than previously thought. The record continues to advance. In 2021, researchers at ETH Zurich created superpositions of gold nanospheres containing billions of atoms. These objects, while invisible to the naked eye, represent the largest objects ever placed in quantum superposition. Each experiment pushes the boundary of what's possible, though we remain many orders of magnitude away from planet-sized objects. What makes planetary superposition so challenging? Consider the numbers involved. Earth contains approximately 10 to the power of 50 atoms. For comparison, the largest quantum superpositions achieved to date involve roughly 10 to the power of 10 atoms, a difference of 40 orders of magnitude. Moreover, Earth constantly interacts with photons from the Sun, cosmic rays, gravitational fields from other planets, and even dark matter particles passing through it. Each interaction potentially causes decoherence. Theoretical physicist Roger Penrose proposed another obstacle: gravity itself might fundamentally prevent large-scale superpositions. His gravitational objective reduction theory suggests that when an object becomes massive enough, the energy difference between superposition states creates an instability in spacetime that forces wave function collapse. According to Penrose's calculations, objects much smaller than planets would spontaneously collapse due to gravitational effects. Testing Penrose's theory is one goal of experiments like the Macro proposal, which aims to test quantum superpositions in the microgravity environment of space, where objects can be better isolated from environmental interference. Interestingly, some interpretations of quantum mechanics avoid the measurement problem entirely. The many-worlds interpretation, proposed by Hugh Everett III in 1957, suggests that superpositions never actually collapse. Instead, all possibilities materialize in separate, non-communicating branches of reality. In this view, not only could planets exist in superposition, but they constantly do, with reality continually branching into all possible configurations. David Bohm's pilot wave theory offers an alternative perspective, proposing that particles always have definite positions, guided by a quantum wave function. This deterministic interpretation eliminates superposition as a physical reality while retaining it as a mathematical description. The Gherardi-Rimini-Weber theory, or GRW theory, takes yet another approach, suggesting that wave functions spontaneously collapse at random intervals, with collapse frequency proportional to an object's mass. For subatomic particles, these collapses might occur once every billion years, while for planet-sized objects, they would happen essentially instantaneously. Beyond these theoretical considerations lie practical obstacles to creating planetary superpositions. To place Earth in a superposition would require complete control over every particle and interaction, an impossible task given the principles of quantum mechanics themselves, particularly Heisenberg's uncertainty principle. Some physicists speculate that if we could somehow achieve the necessary control, the energy requirements would be astronomical. The isolation required would mean removing the planet from all external fields and radiation, effectively separating it from the rest of the universe. Moreover, the question of what constitutes observation remains philosophically thorny. If a planet were in superposition, would the consciousness of organisms living on it constitute a continuous measurement? Does self-interaction within the planet's own gravitational field count as observation? These questions reveal how the measurement problem intertwines with the philosophy of mind and our understanding of consciousness itself. Despite these seemingly insurmountable challenges, the question of macroscopic superposition drives cutting-edge research in quantum foundations. Experiments pushing the quantum classical boundary help refine our understanding of quantum decoherence and potentially reveal new physics. The impossibility of planetary superposition highlights a profound truth: quantum mechanics, despite its extraordinary success in predicting experimental results, may not be the final theory of reality. The search for a theory of quantum gravity, unifying general relativity with quantum mechanics, continues, potentially revealing deeper principles that fully explain the apparent divide between quantum and classical realms. So while we can confidently say that under current physical conditions, an entire planet cannot practically exist in an observable quantum superposition, the theoretical limits continue to be explored. The boundary between quantum weirdness and classical certainty remains one of physics' most fertile grounds for discovery, reminding us that in quantum mechanics, impossibility often conceals profound insights into the nature of reality itself. Negative mass dynamics. Let's venture into one of the most perplexing concepts in theoretical physics, negative mass. What happens when we take Newton's familiar laws of motion and apply them to objects with mass that carries a negative sign? The results are so counterintuitive that they seem to defy our fundamental understanding of reality. First, let's clarify what negative mass would mean. This isn't about antimatter, which has positive mass. Negative mass is a hypothetical form of matter whose mass parameter is literally negative. While we've never observed it in nature, exploring its theoretical implications reveals fascinating paradoxes and possibilities. Consider Newton's second law, F equals m times a. This equation tells us that when we apply a force to an object, it accelerates in the direction of that force. But what if m is negative? Our equation becomes F equals negative m times a, which we can rewrite as negative F equals m times a. This means an object with negative mass would accelerate in the opposite direction to the applied force. Imagine pushing a negative mass object away from you. Instead of moving away, it would accelerate toward you. Throw it to the right, and it moves left. This behavior alone violates our intuitive understanding of how objects should behave. Now let's bring in Newton's law of universal gravitation. The gravitational force between two masses, sub 1 and m sub 2, is given by F equals g times m sub 1 times m sub 2 divided by r squared. If one mass is negative, the gravitational force becomes repulsive rather than attractive. This means a negative mass would be gravitationally repelled by normal matter. But here's where things get truly strange. If both masses are negative, the product of m sub 1 and m sub 2 remains positive, suggesting they should attract each other. However, when we combine this with Newton's second law, we find that negative masses would still move away from each other. This is because the negative mass would accelerate in the direction opposite to the gravitational force. This leads to one of the most famous thought experiments involving negative mass, the runaway motion scenario. Imagine pairing a positive mass with a negative mass of equal magnitude. The positive mass attracts the negative mass, but the negative mass repels the positive mass. However, due to the reversed reaction of the negative mass to forces, both masses would accelerate in the same direction, creating an eternally accelerating system that apparently violates conservation of momentum. Physicists Hermann Bondi and Joseph Weber explored this paradox in 1957, showing that the total momentum of such a system would indeed remain zero despite the continuous acceleration. The positive momentum of one object would be exactly cancelled by the negative momentum of the other. While the kinetic energy of both objects increases without bound, the total energy remains constant because the negative mass object has negative kinetic energy. The implications extend to Einstein's general relativity, where negative mass would create repulsive gravity fields and exotic spacetime geometries. A material with negative mass density would violate the energy conditions that general relativity typically assumes, potentially enabling phenomena like traversable wormholes, warp drives, and time machines. Physicist Kip Thorne has shown that such exotic matter would be necessary to stabilize a wormhole and keep it open for travel. In quantum field theory, certain vacuum states can have negative energy density, suggesting connections to negative mass concepts. The Casimir effect demonstrates that quantum fluctuations can create regions of negative energy density between closely spaced conducting plates. This hints that negative mass energy might exist in some form at the quantum level. Recent experimental work has simulated negative mass behavior in specialized systems. In 2017, researchers at Washington State University created a fluid with negative mass characteristics using ultra-cold rubidium atoms in a Bose-Einstein condensate. When pushed, this fluid exhibited behavior resembling negative mass dynamics, though it wasn't truly negative mass in the gravitational sense. Cosmologists have also considered negative mass as a potential explanation for cosmic mysteries. In 2018, Jamie Farnes of Oxford University proposed a negative mass fluid model as an alternative to dark matter and dark energy, suggesting it could explain both galactic rotation curves and cosmic acceleration with a single substance, a finite space with infinite volume. At first glance, it seems like a mathematical impossibility. How could a space with finite boundaries contain an infinite volume? This paradoxical question challenges our intuitive understanding of space and measure, pushing us to explore some of the most fascinating corners of mathematics, physics, and cosmology. To begin, let's clarify what we mean by finite spatial extent. We're describing a region that's bounded, meaning you can draw a sphere around it or place it within a finite box. Yet within this bounded region, we're proposing the total volume might somehow be infinite. This apparent contradiction forces us to reconsider our fundamental understanding of space itself. The key to resolving this paradox lies in the curvature and topology of space. In Euclidean or flat, three-dimensional space, a bounded region always contains a finite volume. This matches our everyday experience. But mathematics reveals that space need not be Euclidean. When we allow for curved geometries, remarkable possibilities emerge. Consider the Poincaré disk model from hyperbolic geometry. This represents an infinite hyperbolic plane within a finite circular disk. As you move toward the edge of the disk, distances become increasingly compressed according to a specific metric. The boundary itself lies at infinite distance from any interior point, meaning you could never actually reach it in a finite number of steps. Though bounded in one sense, this disk encompasses an infinite hyperbolic area. Extending this concept to 3 dimensions gives us a hyperbolic space that fits within a finite ball, yet contains infinite volume. The mathematician John Nash, C of A Beautiful Mind fame, proved in his embedding theorems that such curved spaces can be mathematically embedded within higher dimensional Euclidean spaces, though potentially with very complex folding patterns. But can such spaces exist physically in our universe, rather than just mathematically? General relativity suggests they might. Einstein's field equations reveal that space itself can curve in response to mass and energy. This curvature affects volume measurements in profound ways. The interior of a black hole presents one tantalizing possibility. According to some solutions of Einstein's equations, particularly the Schwarzschild metric, as you cross the event horizon of a black hole, spatial coordinates undergo a dramatic transformation. The radial dimension effectively switches roles with time, creating what some physicists describe as a waterfall of space. Theoretically, the interior geometry might accommodate infinite proper volume, despite the black hole having a finite external size as measured by its event horizon. Another intriguing possibility comes from cosmological models with unusual topologies. Our universe appears to be expanding, but what if certain regions underwent extremely rapid internal expansion while remaining externally compact? This is not merely speculation. Cosmic inflation theory proposes that our observable universe expanded exponentially in a tiny fraction of a second during its early history. Some theoretical physicists, including Alan Guth and Andrei Linde, have proposed eternal inflation models where pocket universes continually form within a larger multiverse structure. In such scenarios, it's conceivable that a finite region could contain an infinite expanding volume through a process of continuous internal budding of space. The mathematical field of measure theory provides further insights. Georg Cantor's work on transfinite numbers showed that infinity comes in different sizes or cardinalities. The Koch snowflake, a fractal created by repeatedly adding triangular bumps to an equilateral triangle, has finite area but infinite perimeter. Similarly, fractal, like structures in 3 dimensions, could theoretically have finite external extent but infinite internal volume through infinitely nested structures. The Gabriel's horn paradox exemplifies this concept. Created by rotating the curve y equals 1 divided by x, for x greater than or equal to 1 around the x-axis, this shape has finite volume but infinite surface area. Though not exactly what we're looking for, it demonstrates how mathematical objects can have seemingly contradictory finite and infinite properties simultaneously. In quantum field theory, the concept of renormalization deals with infinities that emerge at extremely small scales. The quantum vacuum itself may contain infinite energy density when measured down to arbitrarily small scales. This suggests that even apparently empty, finite regions of space might contain infinite energy, conceptually related to our volume paradox. String theory offers yet another perspective. In some string theory formulations, compact extra dimensions exist at every point in our familiar 3-dimensional space. These extra dimensions are curled up so tightly that we don't notice them in everyday experience, yet they contribute to the total dimensionality of space. Theoretically, these compact dimensions could have extremely complex internal geometries with effectively infinite internal volume, despite their finite external manifestation. Some physicists have even speculated about space folding, technologies based on the Alcubierre metric, a solution to Einstein's equations that allows for effective faster than light travel by contracting space ahead of a vehicle and expanding it behind. While highly speculative, such space manipulations hint at the possibility of engineering regions where internal volume exceeds external boundaries. Recent research in loop quantum gravity suggests that space itself might have a discrete, quantum nature at the smallest scales. If space is fundamentally granular rather than continuous, this could affect how we understand volume at the quantum level, potentially allowing for strange volumetric effects in finite regions. Practically speaking, could we ever create or observe such a space? The energy requirements would be astronomical. Warping space significantly requires either enormous mass, energy concentrations, or exotic negative energy, neither of which we can currently manipulate at the necessary scale. The closest natural candidates remain the interiors of black holes, which are inaccessible to direct observation. Computer simulations offer another perspective. In virtual reality or computational physics, we can create bounded spaces with effectively infinite detail through procedural generation techniques. As you zoom in, new details continuously appear at finer scales. While not truly infinite, such systems can approximate our paradox within computational constraints. What makes this problem so fascinating is how it challenges our intuitive understanding of space itself. We typically think of volume as a straightforward concept, but when we combine ideas from differential geometry, general relativity, quantum field theory, and fractal mathematics, we discover that volume becomes remarkably subtle. The question of finite space with infinite volume stands as a beautiful example of an impossible physics problem, one that seems contradictory at first glance, but when explored with the right mathematical tools, reveals profound connections between geometry, topology, and the physical universe. It reminds us that the cosmos may be stranger and more wonderful than our everyday intuition suggests. A universe with two contradictory laws of physics. Imagine a universe where both Newton's law of gravitation and Einstein's theory of general relativity are equally valid at all scales. In our actual universe, general relativity supersedes Newtonian gravity, especially at high speeds, strong gravitational fields, or vast cosmic scales. But what if both theories were simultaneously true? This creates a profound logical paradox. According to Newton, gravity acts instantaneously across any distance. Two massive objects immediately feel each other's gravitational pull regardless of separation. But according to Einstein, gravitational effects propagate at the speed of light, creating a delay. Information cannot travel faster than light, including gravitational influence. In our hypothetical universe, when a star suddenly disappears, distant planets would both immediately respond Els per Newton and wait for the gravitational waves to arrive Els per Einstein. This is a genuine contradiction, not merely a difference in precision. Physicists have developed several frameworks to handle seemingly contradictory physical laws. One approach comes from quantum mechanics, which already deals with wave-particle duality. The Copenhagen interpretation suggests that a particle exists in multiple states simultaneously until measured. Perhaps our contradictory universe operates on a meta-level version of this principle. The mathematical formalism would be challenging. We might need to develop a superposition of laws, where physical events unfold according to probability distributions drawn from both theories. This resembles how Richard Feynman's path integral formulation describes quantum particles taking all possible paths simultaneously. Another approach draws from Kurt Gödel's incompleteness theorems in mathematics. Gödel proved that any consistent formal system containing basic arithmetic must contain statements that cannot be proven true or false within that system. Perhaps our universe with contradictory laws is fundamentally incomplete. Certain physical scenarios simply become undecidable. The implications for causality are staggering. Einstein's relativity tells us that the order of events can differ depending on the observer's reference frame, but cause must always precede effect. What happens when instantaneous Newtonian gravity meets relativistic causality constraints? We might end up with closed time-like curves, essentially time loops. Physicist John Wheeler proposed the participatory universe concept, suggesting that observers might actively shape reality. In our contradictory universe, perhaps the act of measurement determines which law dominates in a given scenario. The universe might behave like a quantum system that collapses into one state or another depending on observation. Some theoretical physicists have explored doubly special relativity, theories that accommodate seemingly contradictory postulates. These theories modify space-time geometry to maintain multiple invariant scales simultaneously. Our contradictory universe might require similar mathematical innovation. The concept of emergence offers another perspective. In our actual universe, Newton's laws emerge as approximations of Einstein's more fundamental theory in low-energy, slow motion regimes. But what if both laws were equally fundamental? We might need to introduce a meta-law that governs when each base law applies, similar to how thermodynamics emerges from statistical mechanics. String theory suggests extra dimensions might resolve apparent contradictions in physics. Perhaps our contradictory laws operate in different dimensions of a higher dimensional reality, only appearing contradictory when projected onto our limited 4D spacetime. This impossible scenario mirrors real challenges in modern physics. The incompatibility between quantum mechanics and general relativity represents a genuine contradiction in our current understanding. Quantum gravity approaches like loop quantum gravity and causal set theory attempt to resolve these contradictions. The philosopher Karl Popper argued that scientific progress occurs when theories face falsification. Our contradictory universe would be unfalsifiable by definition, existing in a permanent state of paradox. This serves as a reminder that consistency remains a cornerstone requirement for physical law. Perhaps the most profound implication is philosophical. A universe with genuinely contradictory laws suggests limitations to logical reasoning itself. It would require abandoning classical logic for alternatives like paraconsistent logic, which can accommodate contradictions without collapsing into total incoherence. Our own universe's deepest nature might be equally paradoxical, with contradictions we simply haven't yet discovered. The quest to reconcile quantum mechanics with gravity continues to challenge our most brilliant minds, suggesting that reality might be stranger than our logical frameworks can currently accommodate. Faster than light communication, quantum entanglement stands as one of the most bewildering phenomena in modern physics, a connection between particles so profound that Einstein famously called it spooky action at a distance. When two particles become entangled, their quantum states become linked, regardless of the distance separating them. Measure one particle, and its entangled partner instantly adopts a corresponding state, seemingly transmitting information faster than light could travel between them. This naturally raises a tantalizing question. Could we harness entangled particles to create faster than light communication systems, effectively bypassing Einstein's cosmic speed limit? The prospect seems revolutionary: instantaneous communication across galaxies, with no delay whatsoever. The phenomenon that makes this question so compelling is quantum non-locality. When we measure one entangled particle, its partner's state becomes determined instantaneously, even if separated by light years. This correlation appears to violate special relativity's prohibition against information traveling faster than light. However, appearances are deceiving. Despite decades of investigation, physicists have conclusively determined that quantum entanglement cannot transmit usable information faster than light. The fundamental obstacle lies in the random nature of quantum measurement outcomes. Consider a practical example. Alice and Bob each possess one particle from an entangled pair. Alice wants to send Bob a message. She measures her particle, forcing it to assume a definite state up or down. Instantaneously, Bob's particle assumes the correlated state. The problem: Alice cannot control which state her particle will adopt when measured. Quantum mechanics guarantees randomness. If Alice's particle randomly measures as up, Bob's will be down. But Alice had no control over this outcome. For actual communication, Alice needs to control the message. She might try encoding 1 by forcing her particle into the up state and 0 by forcing it down. But quantum mechanics prevents her from controlling these outcomes. They remain stubbornly random. When Bob measures his particle, he observes these random results without knowing if they represent Alice's intended message or mere quantum chance. The no communication theorem, formalized by physicists including Asher Perez and William Wooters, provides rigorous mathematical proof that quantum entanglement cannot transmit information faster than light. The theorem shows that while entangled systems exhibit non-local correlations, these correlations cannot be manipulated to encode messages. Experimental verification comes from tests of Bell's inequalities, which have repeatedly confirmed entanglement's non-local nature while simultaneously demonstrating its uselessness for faster than light communication. Recent Lufol-free Bell tests conducted between 2015-2018 have closed experimental gaps, decisively confirming this conclusion. Interestingly, entanglement does have legitimate applications in quantum communication protocols, but none violate relativity's speed limit. Quantum key distribution uses entangled particles to create unhackable encryption keys, while quantum teleportation transfers quantum states between locations, but both still require classical information transmitted at light speed or slower to complete their protocols. The no signaling principle stands as a deep compatibility requirement between quantum mechanics and special relativity. If faster than light communication were possible via entanglement, it would create causal paradoxes, potentially allowing messages to be sent backward in time from certain reference frames, violating fundamental causality. Proton decay in an eternal universe. In the endless expanse of time, our universe faces a profound question about its ultimate fate. Protons, the building blocks of atomic nuclei, and thus ordinary matter, are remarkably stable particles. Classical physics once considered them eternally stable, but modern grand unified theories suggest they may eventually decay, albeit with lifetimes so vast they boggle the mind, perhaps 10 to the power of 36 years or longer. This creates a fascinating paradox. In an eternal universe, what happens when even the most stable particles eventually vanish? Let's explore this impossible physics problem. Proton decay remains theoretical. We've never observed it. The Super Kamyokan experiment in Japan, containing 50,000 tons of ultra-pure water, has been hunting for proton decays for decades. Their non-observation has pushed the lower bound for proton lifetime beyond 10 to the power of 34 years. Many trillion times the current age of our universe. But suppose protons do decay, perhaps through a process like P plus DE plus Li 0, where a proton decays into a positron and a neutral pion. This would trigger a cascade of consequences across cosmic timescales. First, atomic nuclei would gradually destabilize. Single protons like hydrogen would decay directly, while complex nuclei would undergo sequential decays, releasing radiation and lighter particles. The precise decay pathways depend on specific grand unified theories, but the outcome is inevitable. Baryon number conservation would be violated, and nuclear matter would slowly disappear. After approximately 10 to the power of 40 years, essentially all protons would have decayed. Stars, planets, and all conventional matter structures would have disintegrated. The universe would be dominated by a dilute sea of electrons, positrons, neutrinos, photons, and other decay products. But the story doesn't end there. In an eternal timeline, even electrons may eventually decay or annihilate with positrons. Electron stability isn't guaranteed by the Standard Model, and some theories predict electron decay with lifetimes exceeding 10 to the power of 50 years. Fast forward to 10 to the power of 100 years, and the universe would contain predominantly photons, neutrinos, and potentially dark matter particles. The photon background would consist of incredibly redshifted radiation from ancient decay processes, with wavelengths longer than the current observable universe. The fate of neutrinos adds another dimension. If neutrinos have non-zero rest mass, as current evidence suggests, they would persist but gradually cool to temperatures approaching absolute zero. In an eternally expanding universe, these neutrinos would become so diffuse that interactions between them would become astronomically rare. Remarkably, even after all matter has decayed, the universe doesn't truly become empty. Quantum field theory tells us that space itself contains energy, vacuum energy or dark energy. Quantum fluctuations would still generate particle-antiparticle pairs that materialize briefly before annihilating. These fluctuations represent a kind of quantum foam, a perpetual churning of virtual particles emerging from and dissolving back into the vacuum. In some theoretical frameworks, this vacuum might eventually undergo phase transitions to lower energy states. This could manifest as nucleation of bubbles with different physical laws, potentially creating entirely new pocket universes with different fundamental constants. The ultimate fate depends critically on whether the universe expands forever, as current observations suggest, or eventually recollapses. In an eternally expanding scenario with proton decay, we arrive at a state that physicists Lawrence Krauss and Robert Scherer called the heat death of the universe. A near-perfect vacuum with occasional quantum fluctuations, approaching but never quite reaching absolute entropy maximization. Such a universe exemplifies the second law of thermodynamics taken to its extreme conclusion. A system where all available energy has been converted to unusable forms and all matter has dissolved into radiation, approaching perfect uniformity across incomprehensibly vast distances. A force that is both conservative and non-conservative. In the elegant framework of classical mechanics, forces are typically categorized into two mutually exclusive types, conservative and non-conservative. A conservative force, like gravity or an ideal spring force, conserves mechanical energy, allows for the definition of a potential energy function, and performs zero-net work around any closed path. A non-conservative force, like friction or air resistance, dissipates energy, cannot be expressed as the gradient of a potential, and performs non-zero work around closed paths. These definitions seem fundamentally incompatible, a dichotomy as clear as night and day. Yet in the realm of impossible physics, we confront an intriguing question: can a force possess both conservative and non-conservative properties simultaneously? Can we conceive of a force that both preserves and dissipates energy, that both derives from a potential function and defies such representation? To appreciate the depth of this contradiction, let's first recall the mathematical definition of a conservative force. A force F is conservative if and only if it can be expressed as the negative gradient of a scalar potential function, F equals negative del V. This elegant mathematical property ensures that the work done by the force depends only on the initial and final positions, not on the path taken between them. Consequently, the work done around any closed path must be zero. The closed integral of F dot Drutrar is equal to 0. Non-conservative forces violate these conditions. The work done by friction, for example, depends on the path taken and is always negative for any closed path, reflecting energy dissipation. The closed integral of F dot jar is less than 0. This fundamental distinction between conservative and non-conservative forces appears irreconcilable. However, several physical scenarios suggest intriguing middle grounds that challenge this strict binary classification. Consider magnetohydrodynamics, the study of electrically conducting fluids in magnetic fields. The Lorentz force experienced by charged particles moving through magnetic fields presents an interesting case. While the magnetic component of the Lorentz force, LF equals Q times V cross B, always acts perpendicular to a particle's velocity, performing zero work, and thus appearing conservative in that sense. It nevertheless changes the particle's direction of motion in ways that cannot be derived from a scalar potential. The magnetic force requires a vector potential, making its classification more nuanced than the standard conservative-non-conservative dichotomy. Velocity-dependent forces offer another perspective. Classical mechanics typically defines conservative forces as depending only on position, not velocity. But what about forces that depend on both? The Coriolis force in rotating reference frames influences the path of objects based on their velocity relative to the rotating system. It performs no work directly, acting perpendicular to velocity, yet it cannot be derived from a standard scalar potential due to its velocity dependence. Time-varying potential fields create another fascinating borderland. Consider a particle in a potential well that changes shape over time. The force experienced by the particle can be expressed as the gradient of a potential at any instant, suggesting conservative behavior. Yet the total energy of the particle isn't conserved as the potential evolves, suggesting non-conservative behavior. This time dependence creates a system that defies simple classification. Quantum mechanics introduces additional complexity. The Aharonov-Bohm effect demonstrates that charged particles can be influenced by electromagnetic potentials even in regions where the electric and magnetic fields, the classical forces, are zero. This suggests that potentials may be more fundamental than forces, challenging our classical intuitions about conservative and non-conservative dynamics. Non-holonomic constraints in mechanical systems provide yet another perspective. These are constraints on velocity rather than position, such as a ball rolling without slipping. The forces maintaining such constraints can't be derived from potentials yet don't necessarily dissipate energy in the traditional sense of non-conservative forces. Some researchers have explored quasi-conservative forces that approximately conserve energy under specific conditions, but become dissipative under others. Consider a damped harmonic oscillator with very small damping. Over short time scales or small displacements, the system appears nearly conservative, but over longer periods, the dissipative nature becomes apparent. Emergent phenomena in complex systems offer perhaps the most tantalizing possibilities. In certain non-equilibrium steady states, energy continuously flows through a system, with input balancing output. Locally, some forces might appear to conserve energy, while globally, the system requires constant energy input to maintain its state. The Belgian chemist Ilya Prigogine pioneered work on such dissipative structures, showing how order can emerge from non-equilibrium conditions. Granular materials exhibit particularly interesting behavior. Forces between grains can store energy elastically, like conservative forces, but also dissipate energy through friction and inelastic collisions, unlike non-conservative forces. The collective behavior creates force networks that can switch rapidly between solid, like S energy, conserving, and fluid, like Ls energy, dissipating states. Statistical mechanics offers another perspective through fluctuation dissipation theorems. These relate the response of a system to external perturbations to its intrinsic fluctuations at equilibrium. At the microscopic level, thermal fluctuations can temporarily appear to create or destroy energy locally, even though the statistics over time preserve expected energy conservation laws. Are these examples truly forces that are simultaneously conservative and non-conservative? Not in the strict mathematical sense. The fundamental definitions remain incompatible. However, they reveal that the binary classification misses rich complexities in real physical systems. The conservative-non-conservative dichotomy reflects our mathematical idealization of forces, not necessarily nature's actual organization. Many physical interactions exhibit mixed, conditional, or scale-dependent behaviors that transcend simple categorization. A force might act conservatively in certain dimensions, but non-conservatively in others, conservatively at certain scales, but not at others, or conservatively under certain conditions, but not universally. This impossible problem thus reveals something profound: our physical laws and classifications are models, powerful and precise, but ultimately simplifications of a more complex reality. The question isn't whether a force can be strictly both conservative and non-conservative by our definitions. It cannot, but rather whether nature respects our neat categorical boundaries. It often does not. Modern physics continues to explore these borderlands between idealized categories, revealing that many of our most interesting and important physical phenomena, from turbulence to biological self-organization, from quantum entanglement to cosmological evolution, exist in the rich territory where simple classifications break down. So while we cannot mathematically define a force that is simultaneously fully conservative and fully non-conservative, nature shows us countless examples of forces and systems that display aspects of both. This tension between our definitions and physical reality doesn't represent a failure of physics, but rather an invitation to develop more sophisticated conceptual frameworks that better capture the subtle complexity of the physical world. Infinite chain reaction. Imagine an infinite chain of dominoes stretching to the horizon and beyond, perfectly aligned, each waiting for the touch of its neighbor to fall. Now, here's our impossible physics conundrum. If these dominoes were perfectly rigid, absolutely unyielding to compression, could a single push trigger an infinite cascade instantaneously? Could cause and effect propagate across the boundless chain in zero time? This deceptively simple question forces us to confront profound principles of physics: the nature of rigidity, the speed of information transfer, and the very foundations of causality itself. First, let's understand what perfect rigidity would actually mean. A perfectly rigid body is one that maintains exact distances between all its particles when forces are applied. It deforms exactly zero under any stress. When you push one end of a perfectly rigid object, the other end must move at exactly the same instant. Not almost the same instant, but exactly simultaneously. This means that the disturbance travels with infinite speed through the material. Herein lies our first encounter with impossibility. According to Einstein's special relativity, nothing, no energy, matter, or information, can travel faster than the speed of light, approximately 3 times 10 to the power of 8 meters per second. This cosmic speed limit isn't just a practical constraint, but a fundamental principle of our universe's causal structure. If perfectly rigid objects existed, they would allow for faster than light communication, violating this bedrock principle. When we push an actual physical domino, what really happens? The atoms at the point of contact experience a force that slightly compresses them. This compression creates a pressure wave that propagates through the material at the speed of sound in that medium, typically a few kilometers per second for solids like wood or plastic. This wave carries both energy and information about the disturbance. Only when this wave reaches the far side does that portion know it's been pushed. In our domino scenario, each domino would receive this pressure wave, begin to fall, contact the next domino, and generate a new pressure wave. This creates a cascade that moves at a finite speed, limited by both the mechanical properties of the dominoes and the time required for each to fall and contact the next. But what if we dispensed with reality and imagined truly perfectly rigid dominoes? Let's explore this counterfactual universe and its implications. If perfect rigidity existed, then pushing the first domino would instantaneously move every point within it. The contact point with the second domino would immediately apply force, causing the second domino to begin falling without delay. This process would repeat for every domino in our infinite chain. However, we immediately encounter a logical paradox. If the first domino's motion instantly triggers the second, which instantly triggers the third, and so on through infinity, then the entire infinite set would need to move simultaneously. But this creates a causality paradox. How can the millionth domino fall before the first domino's action has had time to trigger the sequence leading to it? This paradox reflects what mathematicians call a supertask, a countably infinite sequence of operations that would supposedly complete in finite time. Philosophers and mathematicians have wrestled with such concepts since Zeno of Ilia proposed his famous paradoxes over 2,000 years ago. Interestingly, this problem connects to a thought experiment in classical mechanics known as Norton's dome. Philosopher of physics John Norton proposed a scenario where a perfectly rigid ball sits atop a perfectly smooth dome with a specific shape. According to classical mechanics, the ball could either remain at rest indefinitely or spontaneously begin sliding down at any moment, with no apparent cause. This apparent violation of determinism in classical physics highlights how perfect rigidity leads to breakdowns in our physical theories. Even in classical mechanics, where the speed of light doesn't explicitly appear as a limitation, perfectly rigid bodies create problems. The equations governing the behavior of rigid bodies can yield scenarios where forces propagate instantaneously, a property that led to the development of relativistic mechanics. In quantum mechanics, the picture becomes even more complex. The Heisenberg uncertainty principle implies that particles cannot have simultaneously well-defined positions and momenta. For a truly rigid body to exist, all constituent particles would need precisely defined relative positions, potentially violating quantum limits. Quantum field theory offers another perspective. What we perceive as solid matter consists of quantum fields whose excitations, also called particles, interact through force, carrying bosons that travel at or below light speed. These quantum interactions fundamentally prohibit true rigidity. Some physicists have explored whether quantum entanglement might enable instantaneous action at a distance. But detailed analysis shows that quantum correlations cannot transmit usable information faster than light. Even in quantum mechanics, causality remains protected. If we momentarily set aside these physical constraints and imagine a mathematically idealized universe with perfectly rigid bodies, we encounter another problem. An infinite series of dominoes would require infinite energy to set in motion instantaneously. Classical mechanics would require infinite force to accelerate an infinite mass instantaneously, violating energy conservation principles. What's particularly fascinating about this thought experiment is how it bridges seemingly disparate areas of physics and mathematics. The infinite domino problem connects to Zeno's paradoxes, supertasks in philosophy, the impossibility of rigid bodies in relativity, uncertainty principles in quantum mechanics, and energy conservation in classical mechanics. Each perspective reveals another facet of the impossibility. The infinite domino problem also highlights how idealized concepts in physics, like perfect rigidity, instantaneous action, or infinite collections, often lead to paradoxes when pushed to extremes. These paradoxes don't indicate flaws in physics, but rather reveal the boundaries of our idealized models. In practice, what we call rigid objects are actually elastic materials that appear rigid on human scales. Even diamond, one of the hardest known materials, compresses slightly under pressure, with disturbances propagating at its speed of sound, about 12,000 meters per second, fast, but nowhere near infinite. So, can a single push trigger an infinite cascade of perfectly rigid dominoes instantaneously? The answer is a resounding no. The physical universe prohibits both perfect rigidity and instantaneous action across distance. Information, including the mechanical information of "this domino is now falling," can propagate no faster than light. An infinite chain would require infinite time for the cascade to propagate through all members, regardless of how rigid the dominoes might be. This impossible problem ultimately reveals a profound truth: causality in our universe is local and finite. Effects cannot precede causes, and influences cannot propagate with infinite speed. These limitations aren't merely practical constraints we might someday overcome. They are fundamental features of the logical and physical structure of reality itself. An object with simultaneously zero and non-zero rest mass in physics. The concept of an object possessing both zero and non-zero rest mass represents one of the most perplexing paradoxes in our understanding of fundamental particles and forces. Classical physics presents a binary view: objects either have mass or they do not. However, quantum mechanics and relativistic physics reveal a more nuanced reality where this distinction blurs significantly. Consider the neutrino, a subatomic particle that interacts extraordinarily weakly with matter. For decades, the scientific consensus held that neutrinos were massless particles traveling at light speed. However, the 1998 Super Kamiokande experiment in Japan detected neutrino oscillation, the transformation between different neutrino types, which is only possible if neutrinos possess mass. Yet this mass is incredibly tiny, estimated at less than 1/millionth of an electron's mass, placing neutrinos in a curious intermediate state between massless and massive. The paradox extends further when examining composite systems. A box of photons presents an illuminating example. Individual photons are massless particles, yet when confined within a box, the system as a whole possesses rest mass. This emerges from Einstein's energy, mass equivalence, expressed as energy equals mass times the speed of light squared, where the energy of the photons contributes to the overall mass of the system. The structure of the proton reveals an even more startling reality. Modern quantum chromodynamics has established that the quarks within protons contribute only about 1% of the proton's total mass. The remaining 99% comes from the binding energy of the gluon fields, the massless force carriers of the strong nuclear force. Essentially, most of the mass in ordinary matter derives from the energy of massless particles rather than particles with inherent rest mass. In quantum field theory, the Higgs mechanism provides another perspective on this duality. Before interacting with the Higgs field that permeates space, fundamental particles are inherently massless. It is only through this interaction that some particles acquire mass while others remain massless. This transition zone between states questions our understanding of mass as an intrinsic property. String theory introduces additional complexity with its conception of particles as vibrational modes of fundamental strings. In certain string theory models, particles can be massless in higher dimensions, yet appear massive in our four-dimensional spacetime. Kaluza, Klein theory specifically proposes that particles may possess momentum in compactified extra dimensions, which manifests as mass in dimensions we can observe. The boundary between massless and massive becomes even more porous when considering virtual particles. These temporary quantum fluctuations can briefly violate energy conservation principles, allowing normally massless particles to temporarily behave as if they have mass. Recent experimental work at particle accelerators has allowed physicists to examine these theoretical boundaries. The discovery of the Higgs boson at CERN in 2012 confirmed the mechanism by which particles acquire mass, yet raised new questions about the nature of mass itself. The mathematical formalism of quantum field theory accommodates this apparent contradiction through the concept of broken symmetry. In their most fundamental state, the equations describing particles exhibit perfect symmetry where all particles are massless. It is only when this symmetry is broken, through interactions with fields like the Higgs field, that the distinction between massless and massive particles emerges. This paradox of simultaneously zero and non-zero rest mass ultimately reveals that mass itself is not an absolute property, but rather a manifestation of how particles interact with fields permeating spacetime, challenging our classical intuition about the fundamental nature of matter and energy. Moving a magnetic monopole. The theoretical existence of magnetic monopoles represents one of the most tantalizing unsolved puzzles in physics. While conventional magnets always appear with north and south poles paired together, a magnetic monopole would possess only a single isolated magnetic pole, either north or south alone. The motion of a magnetic monopole would be governed by a fascinating set of physical laws that mirror yet fundamentally differ from those governing electric charges. If such particles existed, they would follow modified versions of Maxwell's equations, the cornerstone of classical electromagnetism. In standard electromagnetism, Maxwell's equations include Gauss's law for magnetism, which states that the divergence of the magnetic field is zero, mathematically expressed as the divergence of the magnetic field equals zero. This equation fundamentally prohibits magnetic monopoles. However, if monopoles existed, this equation would be modified to the divergence of the magnetic field equals the magnetic charge density, where the magnetic charge density represents the density of magnetic charge in space, directly paralleling Gauss's law for electric fields. The motion of a monopole would obey a modified Lorentz force law. While an electric charge experiences a force given by charge times the sum of the electric field and the cross product of velocity and magnetic field, a magnetic monopole with magnetic charge would experience force equal to the magnetic charge times the difference between the magnetic field and the cross product of velocity and electric field, divided by the square of the speed of light. This striking duality between electric and magnetic forces would create unique trajectories, unlike anything observed with conventional charged particles. One of the most remarkable properties of monopole motion involves the Dirac quantization condition. In 1931, Paul Dirac proved that if even a single magnetic monopole exists in the universe, all electric charges must be quantized, existing only in discrete amounts rather than continuous values. Specifically, if the magnetic charge of a monopole is represented by one variable, and the elementary electric charge by another, then their product must equal an integer multiple of Planck's constant divided by 2 times pi. This profound connection links the seemingly unrelated phenomena of charge quantization and monopole existence. A moving magnetic monopole would generate an electric field circling around its direction of motion, creating a pattern analogous but perpendicular to the magnetic field produced by a moving electric charge. This electric field would follow an inverse square law, meaning its intensity would decrease with distance from the monopole. The conservation laws governing monopole motion would include both momentum and angular momentum conservation, but with unique implications. When an electric charge interacts with a magnetic monopole, the system possesses angular momentum in the electromagnetic field itself, independent of any mechanical angular momentum of the particles. Energetically, monopoles would carry substantial mass energy. Grand unified theories predict monopole masses approximately 10 to the power of 16 times greater than a proton, equivalent to a microscopic dust particle concentrated in a subatomic volume. This enormous energy density would affect their acceleration and deceleration characteristics in electromagnetic fields. In quantum mechanics, monopoles would behave as point particles with wave-like properties governed by the Schrödinger equation, or the Dirac equation for relativistic cases. Their quantum mechanical interactions would include phenomena like tunneling through potential barriers and discrete energy levels when bound to electric charges. Perhaps most intriguingly, when a magnetic monopole passes through a superconducting loop, it would induce a permanent electric current without any energy input, effectively creating energy from nothing. This apparent violation of energy conservation is resolved by recognizing that the energy comes from the monopole's magnetic field, which must do work against the induced current. Although extensive searches have failed to find conclusive evidence of magnetic monopoles in nature, their theoretical implications remain profound. If discovered, they would complete the symmetry of Maxwell's equations and potentially explain why electric charge exists only in discrete quantities, one of the fundamental mysteries of quantum physics. Entropy reversal in a black hole to entropy, the measure of disorder, the relentless arrow pointing from order to chaos, stands as one of the most fundamental laws of physics. The second law of thermodynamics declares that entropy always increases in any isolated system. Yet what happens if we imagine a black hole absorbing something with negative entropy, challenging this most sacred of physical principles? To unravel this impossible problem, we must first understand entropy at its most fundamental level. In statistical mechanics, entropy measures the number of possible microscopic configurations within a system. More configurations mean higher entropy, more disorder, more randomness. A pristine crystal has low entropy. A heated, vibrating gas has high entropy. The universe itself tends toward increasing disorder, a principle so reliable that it's sometimes called time's fundamental arrow. Black holes complicate this picture dramatically. When Stephen Hawking first calculated black hole thermodynamics, he discovered something revolutionary. Black holes themselves have entropy. The Bekenstein-Hawking entropy is proportional to the event horizon's surface area, not its volume. This means a black hole's entropy depends on its boundary, not its internal structure, a counterintuitive concept that suggests black holes are more than just cosmic vacuum cleaners. Now, enter our impossible scenario, a black hole absorbing negative entropy. What would this mean? Negative entropy would represent spontaneous movement toward increased order. Imagine a heated gas suddenly organizing itself into a perfect crystal, or scattered molecules precisely assembling themselves into a complex machine. Theoretically, negative entropy violates the second law of thermodynamics. It would represent a localized reversal of time's arrow, where chaos spontaneously transforms into order without external input. In our normal universe, this never happens. Eggs don't unscramble, burned papers don't reconstruct themselves, melted ice doesn't spontaneously reform into perfect cubes. But black holes are anything but normal. Their extreme gravitational environments warp our understanding of fundamental physical laws. When a black hole absorbs something with negative entropy, we enter uncharted theoretical territory. One possibility is that the black hole's immense gravitational field would simply negate the negative entropy. The Hawking radiation emitted by black holes already suggests a complex relationship between information, entropy, and gravity. Some theoretical models propose that black holes might act as entropy sinks, regions where standard thermodynamic laws become more fluid. Consider the holographic principle developed by Gerard Hooft and Leonard Susskind. This theory suggests that all the information contained in a volume of space can be represented on its boundary. In a black hole's case, its event horizon. If negative entropy were absorbed, the holographic information might reorganize in ways that preserve overall entropy increase, potentially creating fascinating quantum information dynamics. Quantum mechanical considerations add another layer of complexity. The quantum uncertainty principle means that at microscopic scales, entropy becomes more probabilistic. A system absorbing negative entropy might trigger quantum fluctuations that restore overall entropy balance through seemingly random processes. Some theoretical physicists, like Roger Penrose, have proposed that black holes might play a fundamental role in entropy management within the universe. In Penrose's cyclic cosmological model, black holes could potentially reset or reorganize universal entropy during cosmic transitions. A negative entropy absorption might be part of such a larger entropic cycle. General relativity offers another perspective. The extreme curvature of space-time near a black hole's event horizon could potentially modify how entropy behaves. Some speculative models suggest that within this warped space-time, conventional thermodynamic laws might not apply in straightforward ways. Imagine the absorbed negative entropy as a kind of information density wave. As it crosses the event horizon, gravitational time dilation might stretch or compress this wave in ways that redistribute its entropic properties. The black hole might effectively spread out the negative entropy across its holographic boundary, preventing a direct violation of thermodynamic principles. The information paradox, how information might be preserved or destroyed within black holes, becomes relevant here. If negative entropy represents a form of organized information, its absorption might trigger complex quantum information redistribution mechanisms we don't yet understand. Some theoretical approaches, like loop quantum gravity, suggest that spacetime itself might have discrete, quantized properties at extremely small scales. In such a framework, negative entropy absorption could trigger fascinating quantum geometric reconfigurations that maintain overall entropic balance. Experimental verification remains impossible. We cannot precisely measure entropy transfer across an event horizon, and no known mechanism allows for genuine negative entropy generation. these remain purely theoretical explorations of physics boundaries. What makes this problem fascinating is how it reveals the limits of our current physical understanding. Entropy isn't just a statistical property. It's intimately connected to time's fundamental directionality, information preservation, and the deepest structures of physical law. The scenario of a black hole absorbing negative entropy represents more than just a physics puzzle. It's a thought experiment that probes the very foundations of thermodynamics, quantum mechanics, and our understanding of order and chaos. It reminds us that at the extreme edges of physical reality, our most fundamental laws become more fluid, more mysterious. We cannot definitively say what would happen if a black hole absorbed negative entropy, but in that uncertainty lies the beauty of theoretical physics. Each impossible problem is an invitation to expand our understanding, to peek beyond the current boundaries of human knowledge and imagine what might lie just beyond our comprehension. Photon infinite travel without redshifting. Light travels through the vast cosmic expanse, carrying information from the most distant reaches of the universe. But in an expanding universe, every photon faces an extraordinary challenge, maintaining its energy while traversing immense distances where space itself stretches relentlessly. The concept of cosmic redshift lies at the heart of this problem. As the universe expands, light waves get stretched, increasing their wavelength and decreasing their energy. This is not a gradual option, but a fundamental consequence of cosmic expansion. Each photon's wavelength grows proportionally to the expansion of space between its emission and detection. Consider a photon emitted from a distant galaxy billions of light years away. During its journey, space itself expands, causing the photon's wavelength to lengthen. This isn't the photon moving through space, but space expanding between the photon's points of origin and destination. It's as if the fabric of space-time itself is slowly pulling the light wave apart. The redshift mechanism connects directly to the Doppler effect and Einstein's relativity. As space expands, wavelengths stretch, shifting toward the red end of the electromagnetic spectrum. A photon that began as a high-energy blue light might arrive as a lower-energy red or even infrared wave, having lost energy through this cosmic stretching. To travel infinitely without redshifting would require violating fundamental principles of cosmic dynamics. It would mean a photon could somehow remain immune to the universal expansion, maintaining its exact original energy despite traversing regions where space itself is stretching. Quantum mechanics adds another layer of complexity. Photons are massless particles that always travel at light speed in vacuum. Their energy is intrinsically linked to their wavelength through Planck's relationship EF, where h is Planck's constant and f is the photon's frequency. If the wavelength changes, the energy must change. There's no mechanism for a photon to maintain constant energy while its wavelength transforms. Some theoretical approaches explore exotic scenarios. Could there be regions of space where expansion doesn't occur? Theoretical models, like the cosmic void hypothesis, suggest local regions might have different expansion rates. However, observations consistently show that cosmic expansion is a universe-wide phenomenon, not something that can be locally avoided. The cosmic microwave background radiation provides compelling evidence for universal redshift. Light from the early universe, emitted approximately 380,000 years after the Big Bang, has been stretched from its original high-energy state to microwave frequencies over billions of years. This universal stretching occurs everywhere, making a non-redshifting photon seemingly impossible. General relativity offers deeper insights. The metric tensor describing spacetime explicitly shows how distances between points increase over time. A photon's wavelength is fundamentally tied to this expanding metric. It cannot exist independently of the spacetime geometry surrounding it. Quantum field theory suggests that photons interact continuously with the quantum vacuum. Each interaction potentially modifies the photon's characteristics, making perfect energy conservation across infinite distances thermodynamically improbable. The quantum vacuum itself is dynamic, with virtual particles and quantum fluctuations that would interact with the traversing photon. The energy conservation principle becomes crucial here. In our current understanding of physics, energy cannot be created or destroyed, only transformed. A photon traveling through expanding space must lose energy as space stretches. This isn't a violation, but a fundamental feature of cosmic dynamics. Speculative approaches like string theory or quantum gravity might offer alternative perspectives. Some theoretical models suggest more complex spacetime structures where energy conservation might operate differently. However, no current model provides a mechanism for a photon to maintain its exact original energy across infinite cosmic distances. What makes this problem fascinating is how it reveals the intricate relationship between light, space, and energy. A photon isn't just a particle traveling through space. It's intimately connected to the very fabric of spacetime. Its journey tells a story of cosmic evolution, of space stretching and transforming since the universe's earliest moments. Ultimately, physics suggests that an infinitely traveling photon without redshifting is impossible. The universe's expansion is not just a background feature, but a fundamental dynamic that transforms light's very essence during its cosmic journey. Infinite resistance wire. Electrical resistance is a fundamental property of materials, determining how easily electric current flows through them. But what happens when we push this concept to its absolute limit? A wire with infinite resistance. This seemingly simple scenario unveils profound insights into the nature of electrical current, quantum mechanics, and the fundamental limits of electrical conductivity. Let's begin with Ohm's law, the cornerstone of electrical circuit analysis. This fundamental principle states that current equals voltage divided by resistance. When resistance approaches infinity, something extraordinary happens mathematically. Any finite voltage applied across an infinite resistance would result in zero current. But physics is rarely that simple. At the quantum level, the concept of infinite resistance challenges our classical understanding of electrical conduction. In quantum mechanics, electron transport isn't just about classical current flow, but involves complex wave-like behaviors and tunneling effects. Consider what infinite resistance truly means. It would represent a material where electrons are completely unable to move, a perfect electrical insulator taken to its ultimate extreme. No matter how much voltage is applied, no current could flow through the wire. This sounds straightforward, but the quantum world introduces fascinating complications. Quantum tunneling provides the first hint of complexity. Even in materials with extremely high resistance, quantum mechanics allows for a probabilistic chance of electron transmission. Electrons can potentially tunnel through seemingly impassable barriers, a phenomenon that challenges classical concepts of resistance. The quantum Hall effect offers another perspective. In certain two-dimensional electron systems under strong magnetic fields, resistance can quantize into discrete, precise values. Some of these quantized states approach, but never quite reach, infinite resistance, creating intriguing boundary conditions that defy classical electrical theory. Superconductors provide a counterintuitive contrast. At extremely low temperatures, these materials exhibit zero electrical resistance, allowing current to flow without energy loss. The infinite resistance scenario represents almost the exact opposite, a material where current cannot flow under any circumstances. From a materials science perspective, creating a truly infinite resistance material is impossible. Even the best electrical insulators like diamond or vacuum have some finite, albeit extremely high, resistance. At the atomic scale, perfect isolation becomes mathematically and physically unattainable. Theoretical approaches from solid-state physics suggest that as resistance increases, electron wave functions become increasingly localized. In an infinite resistance scenario, electrons would be completely confined, unable to move between atomic sites. This represents a quantum localization phenomenon where electron mobility approaches zero. The problem connects to fundamental questions in condensed matter physics about the nature of electrical conductivity. What defines the boundary between a conductor and an insulator? How do electron wave functions behave in materials with extreme resistance? Information theory adds another layer of complexity. If no current can flow, how would information be transmitted? The infinite resistance wire becomes a perfect barrier, preventing not just current, but any form of electrical signal transmission. Mathematically, the infinite resistance scenario creates interesting boundary conditions. Circuit analysis breaks down. No current can flow, but the potential for current remains. It's a state of pure potential, where electrical energy exists but cannot be expressed through motion. At the quantum scale, even infinite resistance isn't absolute. Quantum fluctuations and vacuum energy suggest that some probabilistic electron movement might occur, however infinitesimally small. The universe, it seems, abhors absolute boundaries. What makes this problem fascinating is how it reveals the limits of our electrical understanding. An infinite resistance wire isn't just a theoretical curiosity. It's a thought experiment that probes the fundamental nature of electrical conductivity, quantum mechanics, and the subtle boundary between potential and actual energy. In the end, physics suggests that a truly infinite resistance wire remains an impossible concept. The quantum world is too complex, too fundamentally dynamic to allow for absolute electrical isolation. Yet in exploring this impossibility, we gain deeper insights into the remarkable behaviors of electrons, the nature of electrical conductivity, and the profound mysteries that lie at the boundaries of our physical understanding. White hole time reversal. Imagine a cosmic object that does the exact opposite of a black hole. Instead of pulling everything in, it violently ejects matter and light, preventing anything from entering. This theoretical construct, known as a white hole, represents one of the most tantalizing paradoxes in modern astrophysics, a cosmic object that seems to defy the fundamental laws of physics. In classical general relativity, white holes emerge as a mathematical solution to Einstein's field equations, a time-reversed version of a black hole, where a black hole's event horizon allows nothing to escape. A white hole's event horizon prevents anything from entering. It's as if time flows backward, with matter and energy explosively emerging from a single point rather than being consumed by an gravitational abyss. The concept originated from the full mathematical solution of Einstein's field equations. Just as black holes have an event horizon beyond which nothing can escape, white holes would have a similar boundary where nothing can enter. This symmetry is mathematically elegant but physically perplexing. Consider the formation mechanism. Black holes form when massive stars collapse, or when enormous amounts of matter compress into an infinitesimally small point. But how would a white hole come into existence? The time reversal symmetry suggests it would be the exact opposite process, a spontaneous, violent eruption of matter from a singularity. Quantum mechanics complicates this picture further. The time-symmetric nature of fundamental quantum equations suggests that for every process, a time-reversed process should be possible. Yet the arrow of time in our universe seems fundamentally unidirectional. Entropy increases, disorder grows, and time marches relentlessly forward. Some theoretical physicists have explored white holes as potential solutions to cosmic inflation, the rapid expansion of the universe in its earliest moments. Could a white hole represent a kind of cosmic bounce, where matter is explosively ejected from a singularity? The Big Bang itself shares some conceptual similarities with a white hole's behavior. The information paradox adds another layer of complexity. When matter falls into a black hole, information seems to be lost, a fundamental problem in physics. A time-reversed white hole would seemingly need to reconstruct this lost information, violating fundamental thermodynamic principles. Quantum entanglement provides a fascinating perspective. Some theoretical models suggest that black holes might be connected to white holes through quantum bridges, with information preserved through entangled quantum states. This would require exotic physics far beyond our current understanding. Theoretical approaches like loop quantum gravity offer intriguing possibilities. In these models, the singularity at a black hole's center might not be a true endpoint, but a region of extreme quantum transformation. A white hole could represent the other side of this quantum transition, where matter is reconstructed and ejected. The most significant challenge is formation. How could a white hole come into existence? Classical general relativity provides a mathematical solution, but physical mechanisms remain elusive. Would it require a perfect time reversal of a black hole's formation? Could quantum fluctuations create such an improbable scenario? Some speculative cosmological models propose white holes as potential sources of dark energy, the mysterious force driving cosmic expansion. In these theories, white holes would continually eject matter and energy, creating the observed acceleration of the universe's expansion. Observational evidence remains non-existent. No astronomical observations have ever confirmed a white hole's existence. They remain a purely theoretical construct, a mathematical possibility that tantalizes physicists but eludes direct detection. The most profound aspect of white holes is how they challenge our understanding of time itself. They suggest a universe where time could flow backward, where cause and effect might be reversed, where entropy could spontaneously decrease. This is more than a physical impossibility. It's a philosophical challenge to our most fundamental understanding of cosmic order. What makes white holes so captivating is their representation of a cosmic boundary, a theoretical limit where our understanding of physics breaks down. They remind us that at the extreme edges of reality, our most cherished physical laws become more fluid, more mysterious. Physics suggests that white holes, while mathematically possible, face insurmountable obstacles to physical existence. Yet in exploring this impossibility, we gain deeper insights into the nature of time, gravity, and the fundamental structure of our universe. An observer falling into a singularity. The journey to a black hole's singularity represents the ultimate physical limit, a boundary where our understanding of space, time, and physics itself begins to unravel. Can an observer truly describe their fall into this cosmic abyss where the laws of physics break down? At first glance, the answer seems simple. An observer falling into a black hole would experience a remarkable journey. As they approach the event horizon, the point of no return, time and space begin to behave in increasingly bizarre ways. Gravitational time dilation stretches time itself. The surrounding universe would appear to speed up dramatically, with billions of years potentially passing outside while mere moments pass for the falling observer. But describing the actual fall into the singularity, that's where physics encounters its most profound limitations. According to Einstein's general relativity, the singularity represents a point of infinite density where space-time curvature becomes infinite. Mathematically, this means the equations of physics simply break down. Division by zero, infinite gravitational forces, complete breakdown of known physical laws. These are not metaphors, but literal mathematical impossibilities. As our observer crosses the event horizon, they enter a region where conventional physics fails. The tidal forces of gravity become so extreme that they would begin to stretch the observer, a process physicists dramatically call spaghettification. At the event horizon, gravitational differences between the observer's head and feet would become so extreme that they would be literally torn apart at the atomic level. But here's the fascinating paradox. From the observer's perspective, nothing particularly dramatic would seem to happen when crossing the event horizon. There's no visible boundary, no sudden change. The laws of physics appear normal until they absolutely aren't. Quantum mechanics introduces even more complexity. The quantum information paradox suggests that information cannot be truly destroyed, but a singularity seems to represent total information destruction. How can an observer describe something that, by definition, cannot be described by our current physical understanding? Stephen Hawking proposed that quantum effects near the event horizon would create a firewall of intense radiation. This would mean our observer would be destroyed before even reaching the singularity, making any description impossible. Other theories suggest the singularity might not exist at all, replaced by some yet unknown quantum mechanism. Some theoretical approaches, like loop quantum gravity, propose that the singularity might be replaced by a quantum bounce, a region of extreme but finite density where space essentially rebounds. In this model, our observer might survive, but their description would be incomprehensible by current physical understanding. The holographic principle offers another perspective, proposed by Leonard Susskind and Gerard 't Hooft. This theory suggests that all the information about a three-dimensional volume can be encoded on its two-dimensional boundary. For a black hole, this means all information about the interior might be encoded on the event horizon itself, making the internal journey potentially unreal in a fundamental sense. Einstein's equations break down completely at the singularity. Time and space lose their meaning. Cause and effect become meaningless. Our observer would be in a state that cannot be described by any existing physical theory, a true fundamental limit of human knowledge. Some physicists, like Roger Penrose, have suggested that the singularity represents a fundamental reset point, a boundary where our current understanding of physics must give way to a more fundamental theory. It's not just an extreme condition, but a fundamental limit of physical description itself. The most profound answer to whether an observer can describe their fall into a singularity is no, not because they would be destroyed, but because the very concept of description becomes meaningless. Our observer would enter a realm where time, space, information, and physical law itself cease to have their conventional meanings. In this ultimate cosmic limit, observation itself breaks down. The singularity represents more than just an extreme physical condition. It's a boundary of human knowledge, a point where our most fundamental physical theories reach their absolute limit and simply stop making sense. Reversing entropy in a closed system. Imagine a universe where disorder spontaneously transforms into perfect order, where scattered molecules suddenly reorganize, where a shattered glass leaps back together, where time itself seems to flow backward. This is the tantalizing possibility our impossible physics problem explores. Can a perfectly isolated system spontaneously reverse its entropy? The second law of thermodynamics stands as one of the most fundamental principles in physics. It declares that entropy, a measure of disorder, always increases in any isolated system. This law is so reliable that it's often described as time's arrow, pointing inexorably from order to chaos. A drop of food coloring disperses through water. A hot cup of coffee cools. Complexity dissolves into simplicity. But what if we could create a perfect experiment? A completely isolated system with no external influences that might defy this universal law. At the heart of this problem lies statistical mechanics. Entropy isn't just a philosophical concept, but a mathematical measure of possible configurations. A perfectly ordered crystal has low entropy, few possible arrangements. A heated, chaotic gas has high entropy, countless possible molecular configurations. The second law suggests that systems naturally move from fewer to more possible configurations. Theoretically, there's nothing in the fundamental equations of physics that absolutely forbids entropy decrease. At the microscopic level, individual molecular interactions could momentarily reverse, creating a temporary decrease in disorder. The problem is statistical. The probability of such a reversal becomes vanishingly small for macroscopic systems. Consider a thought experiment. Imagine a box of gas molecules perfectly separated, hot molecules on one side, cold on the other. Quantum mechanics allows for statistical fluctuations where molecules might spontaneously cluster. But the probability of this happening for even a small system is astronomically low. To put this in perspective, if you had a box of gas molecules, the time required to see a spontaneous entropy reversal would far exceed the current age of the universe. We're talking about odds so impossibly small that they might as well be zero. Some physicists have explored fascinating theoretical approaches. The fluctuation theorem, developed by Denis Evans and Deborah Searles, provides mathematical insights into entropy fluctuations. It suggests that while entropy decrease is possible, the probability becomes exponentially smaller as the system size increases. Quantum mechanics adds another layer of complexity. At the quantum scale, particles exist in probabilistic states. Some interpretations, like the many worlds theory, suggest that entropy reversals might occur in parallel universes. But in our observable universe, such reversals remain effectively impossible. Information theory provides another perspective. Physicist Rolf Landauer demonstrated that erasing information requires a minimum energy expenditure. This fundamental connection between information and thermodynamics suggests that entropy is more than just a physical property. It's deeply linked to information processing itself. Maxwell's demon, a famous thought experiment, explored similar territory. This hypothetical microscopic being could seemingly violate the second law by sorting molecules. But later work by Landauer and others showed that the demon's information processing itself generates entropy, maintaining the law's integrity. The most profound attempts to understand entropy reversal come from quantum and statistical mechanics. Some theoretical approaches, like loop quantum gravity, suggest that at the most fundamental scales, time and entropy might behave differently than our macroscopic understanding suggests. Recent experiments with ultra-cold quantum systems have shown fascinating near reversals. In 2017, researchers at the University of Chicago demonstrated a quantum system that appeared to partially reverse entropy for extremely brief moments. But these were microscopic, probabilistic events, not true macroscopic reversals. Some speculative cosmological models, like Roger Penrose's cyclic universe theory, propose that the universe might undergo entropy resets during cosmic transitions, but these remain highly theoretical, with no observational evidence. The beauty of this impossible problem is how it reveals the fundamental nature of time itself. Entropy isn't just about disorder, it's about information, probability, and the directional flow of time. A true entropy reversal would require rewriting the most fundamental laws of physics. So can a perfectly isolated system spontaneously reverse entropy? The answer is a resounding no. The statistical impossibility is so extreme that it makes the term impossible seem almost an understatement. Yet in that impossibility lies the profound beauty of physics, a reminder that the universe's fundamental laws are both more reliable and more mysterious than we can imagine. Quantum measurement without observation. At the heart of quantum mechanics lies a profound mystery. The measurement problem. Can we extract information about a quantum system without the act of observation fundamentally altering that system? This seemingly simple question strikes at the very core of quantum theory, challenging our most basic understanding of reality itself. The Heisenberg uncertainty principle stands as our first barrier. Werner Heisenberg demonstrated that certain pairs of physical properties, like position and momentum, cannot be precisely measured simultaneously. The very act of measuring one property inevitably disturbs the other. It's not a limitation of our instruments, but a fundamental characteristic of quantum systems. Quantum systems exist in superposition, multiple states simultaneously, until observation collapses this probabilistic wave function into a single definite state. Imagine an electron spinning both clockwise and counterclockwise at the same time. Measuring its spin forces it to choose one orientation, destroying the original quantum state. But what if we could find a way to peek without looking? Quantum non-demolition measurements offer a tantalizing approach. These techniques attempt to extract information while minimizing system disturbance. By carefully designing measurement protocols, physicists can obtain partial information without completely destroying the quantum state. In 2019, researchers at Yale University demonstrated a remarkable technique using quantum amplification. They managed to detect the presence of a quantum state with minimal disruption by creating a carefully engineered measurement environment. The quantum system was probed indirectly, preserving much of its original coherence. Quantum entanglement provides another fascinating avenue. Entangled particles share instantaneous correlations. Measuring one immediately reveals information about its partner, seemingly without direct observation. Einstein called this spooky action at a distance, highlighting how quantum mechanics defies classical intuitions. The quantum Zeno effect reveals another extraordinary phenomenon. Continuous, weak measurements can actually stabilize a quantum system, preventing its natural evolution. By repeatedly checking a system without fully measuring it, you can effectively freeze its quantum state. A counterintuitive result that challenges our understanding of observation. Some theoretical approaches suggest using quantum error correction codes. These techniques, developed for quantum computing, allow extracting information about a quantum system by spreading its state across multiple entangled particles. The original system remains relatively undisturbed, while information can be indirectly obtained. Weak measurement techniques developed by Yakir Aharonov and colleagues offer another intriguing possibility. These methods extract a small amount of information about a quantum system with minimal disturbance. By taking multiple weak measurements and statistically analyzing the results, researchers can gain insights without fully collapsing the wave function. The holographic principle adds another layer of complexity. Proposed by Gerard Hooft and Leonard Susskind, this theory suggests that all information about a three-dimensional volume can be encoded on its two-dimensional boundary. This implies potential information extraction methods we haven't yet conceived. Quantum ghost imaging represents a remarkable experimental approach. By correlating light that never directly interacts with an object, researchers can construct an image without directly illuminating the target. This technique suggests indirect information extraction might be more possible than classical physics would suggest. Some interpretations of quantum mechanics, like the many worlds interpretation, propose that observation creates multiple simultaneous realities. In this view, information extraction might occur across different quantum branches without fully collapsing a single state. Fundamental limitations remain. The very nature of quantum mechanics suggests that complete information extraction without any disturbance is impossible. Each interaction, no matter how subtle, introduces some level of quantum uncertainty. What makes this problem fascinating is how it reveals the profound difference between classical and quantum information. In the quantum realm, observation isn't passive. It's a fundamental interaction that transforms the system being observed. So can we obtain quantum information without disturbing a system? The answer is a qualified maybe. We can extract partial, probabilistic information with minimal disturbance. But complete, precise measurement without any system alteration remains fundamentally impossible. In this quantum impossibility lies a deeper truth. Reality, at its most fundamental level, is not a fixed, objective thing to be observed, but a delicate dance of probability and interaction. Warp drive with no exotic matter. Imagine traveling faster than light without breaking the fundamental laws of physics, a dream that has tantalized scientists and science fiction enthusiasts for decades. The concept of a warp drive challenges our understanding of space, time, and the very fabric of the universe. At the heart of this fascinating problem lies a fundamental question. Can we create a method of faster than light travel using only known physics, without relying on the mystical concept of exotic matter? The traditional warp drive concept, popularized by science fiction, suggests warping space-time itself to achieve faster than light travel. Proposed by theoretical physicist Miguel Alcubierre in 1994, the original model proposed creating a bubble of spacetime that contracts in front of a spacecraft while expanding behind it. This would theoretically allow a vessel to move faster than light by manipulating the fabric of space itself, rather than moving through space directly. However, the original Alcubierre drive came with a critical problem. It required enormous amounts of negative energy density, or what physicists call exotic matter. This isn't just rare or difficult to produce, it's fundamentally at odds with our current understanding of physics. Exotic matter would need to have negative mass, a concept that violates everything we know about fundamental particle physics and energy conservation. Recent research has begun to chip away at this seemingly insurmountable challenge. Theoretical physicists like Eric Lentz have proposed alternative mathematical models that might circumvent the exotic matter requirement. Lentz's 2021 paper in Classical and Quantum Gravity suggested a potential solution using only positive energy densities, essentially working within the known laws of physics. The key innovation lies in reimagining the shape of the spacetime bubble. Instead of the classic smooth bubble model, Lentz proposed a more complex geometric configuration. By carefully manipulating the energy distribution, he demonstrated a theoretical possibility of creating a warp bubble using only positive energy, the kind of matter and energy we understand and can measure. But challenges remain monumental. The energy requirements are still astronomical. Early calculations suggest that creating even a small warp bubble would require an energy equivalent to the mass, energy of the entire observable universe. To put this into perspective, that's more energy than humanity has produced in its entire history, concentrated into a single moment of propulsion. Some researchers are exploring quantum mechanical approaches. Theoretical work by physicists like Harold White at NASA's EagleWorks laboratory has suggested that quantum fluctuations might provide alternative pathways. They've proposed experiments using interferometry to detect minute spacetime warping effects, though conclusive results remain elusive. The most promising avenue might be understanding spacetime itself more deeply. Quantum gravity theories, which attempt to reconcile general relativity with quantum mechanics, could potentially reveal mechanisms for spacetime manipulation we currently cannot comprehend. Theories like loop quantum gravity and string theory hint at fundamental properties of space and time that might one day enable controlled spacetime manipulation. Interestingly, the challenge of the warp drive mirrors broader questions in theoretical physics. It represents a frontier where our mathematical models bump against the limits of human comprehension. Each theoretical exploration, even if it doesn't immediately solve the faster than light travel problem, pushes the boundaries of our understanding of the universe. The dream of warp drive remains just that, a dream. But it's a dream powered by rigorous mathematical exploration, quantum mechanical insights, and an unquenchable human desire to understand the fundamental nature of reality. As we continue to probe the edges of physics, who knows what revolutionary discoveries await? An infinite sum of finite energy events creating infinite energy. Mathematics allows us to explore fascinating scenarios where infinite series can yield surprising results. Consider a sequence where each event contains a finite amount of energy, but their cumulative sum follows a carefully constructed pattern. Could such a sequence actually generate infinite energy in reality, or is this merely a mathematical curiosity? The classic illustration of this paradox comes from the harmonic series of energy events. Imagine a system where the first event releases 1 unit of energy, the second event releases 1 divided by 2 units, the third one divided by 4 units, the fourth one divided by 8 units, and so on. Mathematically, the sequence looks like 1 plus 1 divided by 2 plus 1 divided by 4 plus 1 divided by 8 plus 1 divided by 16, continuing indefinitely. If we sum these values, something remarkable happens. Despite each individual event contributing less energy than the previous one, the total appears to approach infinity. This convergence challenges our intuitive understanding of energy conservation and the limits of physical systems. Classical thermodynamics provides a strict framework that immediately challenges this possibility. The first law of thermodynamics states that energy cannot be created or destroyed, only transformed. Any system generating infinite energy from finite events would fundamentally violate this cornerstone principle of physics. Yet mathematical series offer tantalizing glimpses of how infinite sums can behave. The harmonic series technically diverges. Its sum approaches infinity, but the rate of divergence is logarithmic. Each additional term contributes less and less, creating a paradoxical accumulation that never quite reaches its apparent limit. Quantum mechanics introduces another layer of complexity. At the quantum scale, energy is not continuous but quantized, existing in discrete packets that cannot be infinitely subdivided. The Planck energy, approximately 10 raised to the power of 19 giga-electron volts, represents a fundamental limit below which our current physical theories break down. This quantum granularity prevents the smooth infinite subdivision suggested by our mathematical series. Information theory provides additional constraints. To generate infinite energy, a system would need to transmit an infinite amount of information, something prohibited by fundamental physical limits. The Bekenstein bound, which limits the information stored in a given region of space, ensures that energy generation cannot escape finite boundaries. Relativity offers another perspective. As energy increases, mass increases according to Einstein's famous equation: energy equals mass multiplied by the square of the speed of light. An infinite energy generation would require infinite mass, another physical impossibility. The extreme gravitational effects would create a black hole long before reaching such a state. Some theoretical approaches explore near infinite energy scenarios through quantum vacuum fluctuations. The quantum vacuum contains enormous potential energy. Estimates suggest a single cubic centimeter contains enough energy to boil all the world's oceans. Yet extracting this energy remains fundamentally impossible due to quantum uncertainty principles. Cosmological models provide intriguing parallels. Inflationary theory suggests the early universe experienced exponential expansion, creating enormous energy from seemingly minimal initial conditions. However, this expansion was finite in duration and constrained by fundamental physical laws. Philosophical interpretations of this problem reveal deeper questions about the nature of infinity. Can potential infinity, a concept in mathematics, translate to actual infinity in physical reality? Philosophers like David Hilbert explored such conceptual boundaries, demonstrating how mathematical infinity differs from physical manifestation. The resolution lies in understanding that mathematical models, while powerful, are not literal descriptions of physical reality. An infinite sum of finite events remains a computational abstraction. Physical systems always contain fundamental limitations: quantum granularity, energy conservation, and information constraints that prevent true infinite energy generation. What makes this impossible problem fascinating is how it reveals the profound boundary between mathematical abstraction and physical reality. Mathematics allows us to explore conceptual spaces that physical systems cannot inhabit. Each seemingly paradoxical scenario becomes an invitation to understand the deeper structures governing our universe. Ultimately, the attempt to generate infinite energy from finite events fails. The universe maintains its fundamental constraints, ensuring that energy remains a conserved, quantized phenomenon subject to precise physical laws. Our mathematical imagination can explore infinite possibilities, but physical reality always imposes its own elegant limitations. Schrödinger's cat in an infinite box. Quantum mechanics has always danced on the razor's edge between the intuitive and the impossible. Erwin Schrödinger's famous thought experiment: a cat simultaneously alive and dead until observed. now takes an even more bizarre turn. What happens when we place this quantum feline in a box with infinite potential walls, pushing the boundaries of quantum confinement to their absolute limit? In standard quantum mechanics, a particle in a finite potential well is constrained by walls that create discrete energy levels. Imagine those walls extending to absolute infinity, a confinement so perfect that escape becomes mathematically impossible. Our cat now finds itself trapped in the ultimate quantum prison. Classical physics would simply describe this as complete confinement. An infinite potential barrier means zero probability of escape, absolute containment. But quantum mechanics operates by fundamentally different rules. The wave function of a quantum system doesn't respect classical boundaries in the same way. The time-independent Schrödinger equation for an infinite potential well creates a fascinating mathematical scenario. Unlike finite wells with discrete energy levels, the infinite well imposes the most extreme boundary conditions possible. The wave function must be exactly zero at the walls, a perfect cancellation of probability. For our quantum cat, this means something profoundly strange. Its wave function would be constrained to generate perfectly standing waves within the infinite box. Each possible state becomes a precise mathematical solution, with nodes exactly at the infinite walls. The cat exists not as a discrete object, but as a probabilistic wave pattern perfectly synchronized with its infinitely constrained environment. Quantum uncertainty becomes absolute in this scenario. The cat isn't just in an indeterminate state. It becomes a pure wave of probability, its position and momentum defined by mathematical constraints rather than physical observation. It's not alive or dead, but a mathematical abstraction perfectly distributed across the infinite potential well. The energy levels in such an infinite well follow a precise mathematical progression. Each state becomes increasingly compressed, with energy levels approaching an asymptotic limit. Our cat would exist in a series of increasingly high frequency wave states, each more tightly constrained than the last. Fundamental quantum principles like the uncertainty principle become intriguingly extreme. With infinite walls preventing any possible momentum transfer, the positional uncertainty of the cat would approach absolute limits. It becomes simultaneously everywhere and nowhere within the box, a pure quantum probability distribution. Some interpretations suggest this infinite confinement might create a form of quantum immortality. Since the wave function never completely collapses and escape is mathematically impossible, the cat exists in a perpetual state of quantum superposition. It's not alive or dead, but a pure quantum entity defined by mathematical probability. The philosophical implications become mind-bending. Is the cat still a cat, or has it transformed into something entirely different? A pure quantum object defined by wave functions and probability distributions, the boundary between classical object and quantum abstraction completely dissolves. Practically, such infinite confinement is impossible. Real materials always have finite properties. Even the strongest containment has limits. Quantum tunneling always provides a non-zero probability of escape. The infinite potential well remains a mathematical idealization, not a physical reality. What makes this impossible problem fascinating is how it reveals the profound difference between classical and quantum understanding. Our intuitive concept of an object breaks down when pushed to quantum extremes. The cat becomes less a living creature and more a pure mathematical construct, a wave of probability perfectly synchronized with its infinite environment. This thought experiment reminds us that quantum mechanics isn't just a description of reality, but a fundamental reimagining of what reality can be. At the edges of physical understanding, objects become probability, observation becomes creation, and infinity reveals itself as a mathematical playground where our classical intuitions completely fail. Time travel grandfather paradox. The grandfather paradox represents the ultimate logical conundrum of time travel. A scenario that has tantalized physicists, philosophers, and science fiction enthusiasts for generations. Imagine traveling back in time and deliberately preventing your own grandparents from meeting, thus eliminating the very possibility of your own birth. What happens in such an impossible circumstance? Do you instantly vanish, continue to exist, create an entirely new timeline? At its core, the paradox reveals the fundamental logical impossibility of backwards time travel as we traditionally conceive it. The scenario creates an irresolvable causal loop. If you prevent your grandparents from meeting, you should never have been born to travel back in time in the first place. Yet, if you were never born, how could you have traveled back to prevent your own existence? Theoretical physics offers several potential resolutions to this mind-bending scenario. The multiple worlds interpretation of quantum mechanics suggests the most intuitive solution. When you travel back in time and alter the past, you create an entirely new timeline, a parallel universe branching off from the original. In this model, you would continue to exist as a time traveler in this new timeline, while your original timeline remains unchanged. Another approach comes from the consistent histories interpretation, which proposes that time travel might be fundamentally self-consistent. Under this model, any attempt to change the past would inevitably fail. If you traveled back to prevent your grandparents meeting, some improbable but ultimately inevitable series of events would prevent you from succeeding. A sudden illness, a missed connection, an unexpected interruption. Renowned physicist Igor Novikov proposed the Novikov self-consistency principle, which argues that time travel is possible, but paradoxes are impossible. In this view, the laws of physics would somehow prevent any action that could create a logical contradiction. You might find yourself unable to pull the trigger, or your bullet might mysteriously miss, or some other intervention would ensure your grandparents' meeting remains intact. Quantum mechanics adds another layer of complexity. The observer effect suggests that the mere act of observation changes a system. In a time travel scenario, your presence in the past would fundamentally alter the quantum state of that moment, creating unpredictable and potentially impossible outcomes. Some theoretical physicists, like Kip Thorne, have explored more exotic solutions involving closed time-like curves, theoretical paths through spacetime that return to their starting point. These solutions suggest that time might be more malleable than our linear perception suggests, with causality operating in ways we cannot easily comprehend. The many worlds interpretation offers perhaps the most philosophically satisfying resolution. In this model, every possible outcome exists simultaneously in different universes. Your attempt to prevent your birth would simply create a new universe where you exist as a time traveler, while your original universe remains unchanged. General relativity provides mathematical frameworks that suggest time travel might be theoretically possible through extreme spacetime curvature, such as rotating black holes or wormholes. However, the energy requirements would be astronomical, far beyond any current technological capabilities. Some researchers have explored quantum mechanical approaches that might resolve the paradox. Quantum entanglement and superposition suggest that information and causality might operate differently than our classical understanding suggests. Your attempt to change the past might exist in a state of quantum superposition, simultaneously successful and unsuccessful. The grandfather paradox ultimately reveals more about the nature of causality, time, and human understanding than about time travel itself. It demonstrates the limits of linear thinking about time and causation. Our perception of time as a simple, unidirectional arrow may be fundamentally incomplete. What makes this problem so fascinating is how it exposes the profound mysteries at the intersection of physics, logic, and philosophy. Time travel challenges our most basic assumptions about cause and effect, about the nature of reality itself. Each proposed solution reveals more about the complex, interconnected nature of spacetime than about the specific mechanics of time travel. Ultimately, the grandfather paradox remains unresolved. It stands as a testament to the limits of human understanding, a reminder that the universe contains mysteries far more complex than our current theories can explain. Whether through multiple universes, quantum mechanics, or yet undiscovered physical principles, the paradox continues to challenge our most fundamental assumptions about reality. Perfectly confined quark. Quantum chromodynamics presents one of the most fascinating mysteries in particle physics, the absolute impossibility of isolating a single quark. No matter how much energy you invest, no matter how sophisticated your containment strategy, a quark will always refuse to exist in isolation. A phenomenon known as color confinement. At the heart of this impossibility lies the strange behavior of the strong nuclear force. Unlike electromagnetic forces that weaken with distance, the strong force between quarks actually increases as they're pulled apart. Imagine trying to separate two quarks connected by a quantum rubber band that becomes progressively more rigid the further you stretch it. Mathematically, this behavior emerges from the fundamental equations of QCD. As quarks are separated, the energy required increases quadratically, approximately like a linear spring constant. At a certain point, the energy invested in separation becomes so great that it's more energetically favorable to create new quark-antiquark pairs rather than completely isolate a single quark. If you attempt to pull quarks apart, something remarkable happens. The energy invested in separation becomes so immense that it spontaneously generates new quark-antiquark pairs. These pairs materialize from the quantum vacuum, effectively preventing the original quarks from becoming truly isolated. It's as if the universe itself conspires to prevent quark isolation. Experimental evidence confirms this theoretical prediction. Particle accelerators have repeatedly demonstrated that when you try to separate quarks, you don't get individual quarks. Instead, you create new hadrons. Quarks always emerge bundled together in composite particles like protons or mesons, never as standalone entities. The quantum mechanical explanation involves color charge, a fundamental property analogous to electrical charge, but with crucial differences. While electrical charges can exist independently, color charges must always combine to form colorless combinations. A quark must always be accompanied by other quarks that cancel out its color charge, like red, green, and blue combining to form white. Theoretical models suggest that if you could somehow apply infinite energy to separate quarks, you would create a phenomenon called a flux tube, a string-like configuration of gluon fields connecting the quarks. This flux tube would have a constant tension, making quark separation increasingly difficult as distance increases. Some theoretical approaches, like lattice QCD simulations, have explored the mathematical boundaries of quark confinement. These computational models confirm that no matter how complex the containment strategy, quarks will always find a way to avoid complete isolation. Quantum field theory provides another perspective. The vacuum itself isn't empty, but filled with quantum fluctuations, a roiling sea of virtual particles constantly appearing and disappearing. These fluctuations make true isolation impossible, as the quantum vacuum will always intervene to prevent absolute separation. The most advanced particle accelerators and colliders have pushed this principle to extreme limits. Even in the most energetic particle collisions, quarks emerge in bound states, never as free particles. The Large Hadron Collider, capable of recreating conditions moments after the Big Bang, has never observed a truly isolated quark. Theoretical physicists have explored exotic scenarios, quantum teleportation, extreme energy states, even speculative higher dimensional configurations. Yet each approach ultimately falls prey to the same fundamental constraint: quarks must remain confined. Some researchers have proposed that quark confinement might relate to deeper symmetries in quantum field theory. The phenomenon might connect to more fundamental principles about how information and energy behave at the quantum scale, a window into the deeper structures of physical law. What makes quark confinement so fascinating is how it represents a fundamental limit of physical reality. It's not just a practical constraint, but a deep principle that emerges from the very structure of quantum mechanics. The universe seems to have built in rules preventing certain kinds of absolute isolation. The perfectly confined quark remains an impossible dream, a theoretical boundary that reveals the profound interconnectedness of quantum systems. No matter how clever the approach, no matter how advanced the technology, a single quark will always refuse to stand alone. Big Crunch vs. Heat Death. Imagine a universe caught in an impossible limbo, simultaneously expanding and contracting, racing toward both total dissolution and ultimate collapse. This isn't just a theoretical curiosity, but a profound exploration of cosmic fate that challenges our most fundamental understanding of universal physics. The Big Crunch and Heat Death represent two diametrically opposed cosmic scenarios. In the Big Crunch model, the universe's expansion eventually halts and reverses, with gravity pulling everything back into an infinitesimally dense point, a cosmic implosion. The heat-death scenario presents the opposite fate: eternal expansion, where the universe gradually cools, matter disperses, and energy becomes so evenly distributed that no work can be performed. Typically, these scenarios depend on the universe's total matter and energy density. If density exceeds a critical threshold, gravity wins and the universe contracts. If density is below this threshold, expansion continues forever. But what if the universe could somehow exist in both states simultaneously? Such a scenario would require violating fundamental principles of general relativity. The universe's curvature, whether flat, closed, or open, determines its ultimate fate. A closed universe curves back on itself like a sphere's surface, while an open universe extends infinitely like a plane. Our current cosmological measurements suggest the universe is remarkably close to flat, with a slight tendency toward openness. Quantum mechanics introduces fascinating complications. At the quantum scale, particles can exist in multiple states simultaneously through superposition. Could the universe itself exhibit a similar quantum ambiguity? Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that multiple cosmic states might coexist across different quantum branches. Imagine a cosmos where space-time itself becomes a quantum superposition, simultaneously contracting and expanding, Regions of space might experience gravitational collapse while others continue expanding, creating a patchwork universe that defies classical categorization. Quantum entanglement might allow instantaneous communication between these seemingly contradictory cosmic regions. String theory offers another perspective. In some multiverse models, our universe could be a membrane existing alongside other dimensional spaces. These branes might interact in ways that create localized regions of contraction and expansion, blurring the line between big crunch and heat death. The energy requirements for such a scenario are mind-boggling. Maintaining simultaneous expansion and contraction would require extraordinary conditions that violate known conservation laws. The total energy of the universe must remain constant, yet this impossible state would seemingly require energy to flow in contradictory directions. Gravitational dynamics become even more complex. For contraction and expansion to coexist, gravity would need to simultaneously attract and repel. A physical impossibility under current understanding. Dark energy, which drives cosmic expansion, would need to be manipulated in ways that defy our current cosmological models. Entropy presents another fundamental challenge. The second law of thermodynamics suggests that entropy always increases. A universe simultaneously experiencing big crunch and heat death would require entropy to move in multiple directions, creating a thermodynamic paradox. Some theoretical physicists have explored cyclic universe models where big crunch and heat death might alternately occur. Roger Penrose's conformal cyclic cosmology suggests universes might repeatedly expand and contract, with each cycle losing information but maintaining some fundamental structure. But even these models don't propose true simultaneous contraction and expansion. Quantum gravity theories hint at more exotic possibilities. At the tiniest scales, where quantum mechanics and general relativity intersect, spacetime might become so flexible that seemingly contradictory states become momentarily possible. These quantum fluctuations could create brief windows where cosmic expansion and contraction coexist. The most profound implication of this impossible scenario is philosophical. It challenges our understanding of causality, suggesting that fundamental physical laws might be more fluid than we imagine. If a universe could simultaneously contract and expand, what other impossible states might exist beyond our current comprehension? Ultimately, our universe appears to reject such contradictions. Physical laws emerge from fundamental symmetries that prevent simultaneous opposing states. The big crunch and heat death remain mutually exclusive scenarios, each representing a potential cosmic destiny determined by the universe's total energy and matter distribution. Yet the very impossibility of this scenario reveals the beauty of theoretical physics, an endless exploration of conceptual boundaries where imagination meets mathematical rigor, always pushing toward deeper understanding of reality's fundamental nature. Gravitational Blueshift infinity. Imagine dropping a photon, a particle of light, toward a black hole. As it descends into the increasingly intense gravitational field, something extraordinary happens. The photon's frequency increases, shifting toward the blue end of the spectrum. But what if this blue shift continues, approaching the black hole's event horizon? Could the photon's energy theoretically become infinite? General relativity provides the key to understanding this paradox. Einstein's theory reveals that gravity doesn't just attract masses. It warps spacetime itself. Near a black hole, spacetime becomes so severely curved that the very concept of energy becomes problematic. A photon falling toward a black hole experiences gravitational redshift in reverse, a gravitational blueshift that appears to increase its energy without limit. The mathematics of gravitational Blueshift stems from the gravitational redshift formula, which relates a photon's observed frequency to its distance from a massive object. As the photon approaches the event horizon, its frequency should increase exponentially. Classical calculations suggest the photon's energy would approach infinity as it nears the event horizon's boundary. However, physical reality intervenes where pure mathematics breaks down. Quantum mechanics introduces fundamental limitations that prevent infinite energy scenarios. The Planck energy, approximately 1019 GeV, represents a fundamental energy scale beyond which our current physical theories become meaningless. No matter how intense the gravitational field, a photon cannot exceed this quantum energy limit. Black hole physics adds another layer of complexity. Stephen Hawking's work revealed that black holes aren't truly black, but emit radiation through quantum effects. As a photon approaches the event horizon, quantum uncertainty becomes dominant. The photon's behavior transitions from classical wave-like properties to quantum probabilistic interactions that defy simple energy calculations. Consider the perspective from different reference frames. An observer far from the black hole would see the photon's frequency increasing as it falls. But an observer falling alongside the photon would experience no such blueshift. This relativistic paradox highlights how gravity warps our fundamental understanding of energy and observation. The holographic principle offers another fascinating perspective. Developed by physicists like Leonard Susskind, this theory suggests that all information in a volume of space can be represented on its boundary. In a black hole's case, the event horizon, the photon's apparent energy increase might be an information transformation rather than a true energy increase. Quantum field theory provides additional insights. Photons aren't simply particles, but excitations of underlying quantum fields. As these fields interact with extreme gravitational environments, their behavior becomes increasingly complex. The notion of a photon's energy becomes less meaningful at the quantum scale near a black hole. Some theoretical approaches, like loop quantum gravity, suggest that spacetime itself becomes discrete at extremely small scales. Near the event horizon, space might fragment into quantum units that prevent the smooth energy increase suggested by classical calculations. These quantum geometric effects would interrupt the infinite blueshift scenario. The information paradox becomes relevant here. How does information, and by extension energy, behave at the boundary of a black hole? Theoretical physicists like Hawking and Penrose have shown that black holes fundamentally challenge our understanding of energy conservation and information preservation. Experimental verification remains impossible. No instrument could survive measurements near a black hole's event horizon. These explorations remain purely theoretical, pushing the boundaries of our physical understanding. What makes this problem fascinating is how it reveals the limits of our physical theories. The attempt to calculate a photon's infinite energy exposes the breakdown of classical physics at extreme gravitational conditions. It's a reminder that our most fundamental physical laws are approximations, breaking down at the most extreme cosmic scales. We cannot definitively say what happens to a photon's energy at a black hole's event horizon, but in that uncertainty lies the beauty of theoretical physics. Each impossible problem is an invitation to expand our understanding, to peek beyond the current boundaries of human knowledge, and imagine what might lie just beyond our comprehension. Ultimately, the gravitational blueshift infinity remains a theoretical paradox. Physical reality imposes limits that prevent infinite energy scenarios, reminding us that the universe maintains its elegant constraints even in the most extreme environments. A particle with both spin states measured. At the heart of quantum mechanics lies a profoundly counterintuitive principle. The act of measurement fundamentally alters the system being measured. Nowhere is this more dramatically illustrated than in the case of a spin half-particle, a quantum system that seemingly defies our classical understanding of reality. Consider a single electron, the quintessential spin one-half particle. In quantum mechanics, this particle doesn't simply spin or down like a classical top. Instead, it exists in a superposition of both states simultaneously, a ghostly condition where both spin up and spin down coexist until the moment of measurement. The famous Stern-Gerlach experiment, first conducted in 1922, revealed this bizarre quantum behavior. When a silver atom passes through a magnetic field, it's deflected either up or down, but never both simultaneously. This experimental result hints at the deeper quantum principle. Measurement collapses the wave function, forcing the particle into a single, definitive state. Heisenberg's uncertainty principle provides the fundamental explanation. For spin one-half particles, measuring spin along one axis inherently disturbs the particle's spin along other axes. This isn't a limitation of measurement technology, but a fundamental property of quantum systems. The more precisely we determine one property, the less precisely we can know complementary properties. Mathematically, spin states are represented by quantum wave functions, complex mathematical descriptions that encode all possible states of a particle. Before measurement, a spin one-half particle exists in a probabilistic superposition. The wave function gives us probabilities of obtaining spin up or spin down, but not the actual state itself. Quantum mechanics describes this using the Bloch sphere, a geometric representation of a two-level quantum system. Before measurement, the particle's state can be anywhere on the surface of this sphere. Measurement forces the state to one of two poles, spin up or spin down, with probabilities determined by the initial state's position. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that both measurement outcomes occur, but in separate, non-communicating universe branches. In this view, the particle does experience both spin states, just not within a single observable reality. Quantum entanglement adds another layer of complexity. If two particles are entangled, measuring the spin of one instantaneously determines the spin of the other, regardless of distance. This spooky action at a distance, as Einstein called it, further challenges our classical understanding of measurement and reality. Experimental attempts to simultaneously measure both spin states inevitably fail. The act of measurement itself forces a choice. Each measurement apparatus can only detect one state, and the very process of measurement destroys the delicate quantum superposition. Advanced quantum eraser experiments have shown that even the possibility of measuring a property can affect a quantum system's behavior. The mere potential for measurement introduces uncertainty, a phenomenon known as quantum interference. At the quantum scale, measurement is not a passive observation, but an active interaction. The measuring device and the particle become temporarily entangled, with the device's macro-scale classical state forcing the quantum system into a definitive configuration. Some theoretical physicists have explored thought experiments involving indirect or weak measurements, techniques that might extract information about a quantum system with minimal disturbance. However, these approaches still cannot simultaneously resolve both spin states with complete certainty. The fundamental limitation isn't technological, it's intrinsic to the nature of quantum mechanics. A spin 1/2 particle cannot have both spin, up, and spin, down measured simultaneously, because the act of measurement itself is a process of selection, not observation. This seemingly impossible problem reveals a profound truth about quantum reality. At the smallest scales, nature operates not through definitive states, but through probabilities and potentialities. Our classical intuition of discrete, well-defined properties breaks down, replaced by a more fluid, interconnected understanding of physical reality. The spin 1/2 particle stands as a beautiful reminder that the universe is far stranger than our everyday experience suggests. Each measurement is not just an observation, but a moment of creation, where possibility collapses into a single, momentary reality. Infinite heat engine efficiency. Imagine a machine that could extract unlimited energy from a single heat source, a perpetual motion device that defies the fundamental laws of thermodynamics. Our impossible physics problem challenges the very foundation of energy conversion. Can a heat engine achieve 100% efficiency, drawing infinite work from a single reservoir of thermal energy? The dream of unlimited energy has tantalized inventors and engineers throughout history. A perfect heat engine would convert all available thermal energy into mechanical work, eliminating energy losses and providing an inexhaustible power source. But this seemingly simple concept crashes headlong into the second law of thermodynamics, one of the most fundamental principles governing energy in our universe. To understand why this is impossible, we must first explore how heat engines actually work. A typical heat engine operates between two temperature reservoirs, a hot source and a cold sink. The temperature difference allows energy to be converted into work. As heat flows from the hot reservoir to the cold reservoir, some of that energy can be transformed into mechanical motion. The efficiency of a heat engine is limited by the Carnot cycle, developed by French physicist Sadi Carnot in 1824. The Carnot efficiency represents the maximum theoretical efficiency possible for any heat engine operating between two temperature reservoirs. It's calculated as the difference between hot and cold reservoir temperatures divided by the hot reservoir temperature. Mathematically, this means a perfect heat engine could never convert 100% of thermal energy into work. There will always be some energy lost to the cold reservoir. Even a theoretical perfect heat engine can only approach, but never reach, 100% efficiency. Consider the implications of an infinite efficiency heat engine. Such a machine would require extracting unlimited mechanical work from a single heat source without any temperature difference. This violates the fundamental principle that heat spontaneously flows from hot to cold, never the reverse without external work. Quantum mechanics provides another barrier. At the microscopic level, energy transfer isn't continuous but occurs through discrete quantum interactions. The quantum of action, Planck's constant, ensures that perfect energy conversion is mathematically impossible. Quantum uncertainty introduces fundamental limitations on precise energy measurements and transfers. Information theory offers additional insights. To extract work from a heat reservoir, a machine must gather and process information about molecular energy states. The act of measuring and processing this information requires energy expenditure. This means any attempt to extract unlimited energy would require more energy than the system could produce. A fundamental contradiction. Statistical mechanics reveals why single-temperature heat engines fail. Thermal energy represents the random motion of particles. To extract work, you need a temperature gradient, an organized flow from hot to cold. A single uniform temperature reservoir contains no potential for directed work. It's like trying to generate electricity from a uniformly heated room. Some theoretical approaches have explored exotic scenarios. Quantum heat engines utilizing quantum coherence or entanglement suggest marginal improvements in efficiency. Researchers have developed theoretical machines operating near quantum limits, but these remain far from infinite efficiency and still obey fundamental thermodynamic constraints. The Bekenstein bound, a limit on information storage in a finite region, provides another fundamental constraint. Any attempt to extract unlimited energy would require storing infinite information, which is physically impossible within our current understanding of physics. Deep connections emerge between energy, information, and entropy. An infinite efficiency heat engine would require reducing entropy to zero, creating perfect order from thermal randomness. But entropy always increases in closed systems, making such perfect organization fundamentally impossible. Philosophical interpretations reveal deeper truths. The quest for unlimited energy reflects humanity's desire to transcend natural limitations. Yet these very limitations, embodied in thermodynamic laws, ensure the universe's fundamental stability and complexity. What makes this impossible problem fascinating is how it illuminates the profound constraints governing energy transformation. Our universe permits extraordinary complexity and potential, but always within precise, elegant boundaries. The impossible heat engine reminds us that limitations aren't obstacles, but the very conditions that make meaningful energy conversion possible. The dream of unlimited energy remains just that, a dream. Our heat engines will always be imperfect, always lose some energy to the surrounding world. But in that imperfection lies the beautiful complexity of physical reality, a universe far more interesting than any perpetual motion fantasy. A theory of everything that is incomplete. The quest for a theory of everything represents humanity's most ambitious scientific endeavor. A singular, elegant framework that would seamlessly describe all fundamental physical interactions, from the tiniest quantum fluctuations to the vast expanses of cosmic structures. But what if such a theory, despite its comprehensiveness, was fundamentally and intentionally incomplete? Historically, our understanding of physics has progressed through increasingly comprehensive theories that unify previously disparate phenomena. Newton united terrestrial and celestial mechanics. Einstein connected space and time through relativity. Quantum mechanics revealed the probabilistic nature of subatomic interactions. Yet each breakthrough simultaneously illuminated and exposed deeper mysteries. A truly complete theory of everything would need to reconcile quantum mechanics and general relativity, two pillars of modern physics that describe reality at different scales, but remain mathematically incompatible. Quantum mechanics governs the microscopic world of particles, while general relativity explains gravitational interactions and cosmic structures. Their fundamental mathematical languages seem irreconcilable. String theory emerged as one of the most promising candidates for a unified framework. By proposing that fundamental particles are actually tiny vibrating strings in multiple dimensions, it offers a potential bridge between quantum and relativistic descriptions. Yet string theory remains frustratingly abstract, with multiple versions and no definitive experimental verification. The incompleteness wouldn't stem from mathematical or conceptual gaps, but from fundamental limitations in our ability to observe and comprehend reality. Kurt Gödel's incompleteness theorems in mathematics suggest that any sufficiently complex logical system contains statements that cannot be proven within that system. Physics might face an analogous limitation, a theory so comprehensive that it inherently contains unresolvable uncertainties. Quantum mechanics already demonstrates such intrinsic limitations through the uncertainty principle. We cannot simultaneously know a particle's precise position and momentum. A theory of everything might similarly contain built-in epistemological boundaries, areas of fundamental uncertainty that are not flaws, but essential characteristics of the theory itself. Consider the measurement problem in quantum mechanics. Different interpretations, Copenhagen, many worlds, pilot wave, offer competing explanations for quantum behavior. A truly comprehensive theory might require acknowledging multiple valid perspectives simultaneously, embracing uncertainty as a feature rather than a bug. Computational complexity offers another perspective. Some problems are theoretically solvable, but practically impossible to compute. A theory of everything might be mathematically coherent, yet so complex that complete verification becomes computationally intractable. The theory could be fundamentally true while remaining beyond our computational capabilities. Information theory suggests another fascinating limitation. The Bekenstein bound limits the information that can be stored in a given region of space. A theory of everything might be constrained by fundamental information processing limitations, creating inherent blind spots in our understanding. Philosophical considerations add depth to this concept. Thomas Kuhn's work on scientific paradigms suggests that revolutionary scientific theories don't just add knowledge. They transform how we conceptualize knowledge itself. A truly comprehensive theory might be incomplete precisely because it requires us to reimagine our fundamental understanding of reality. Some physicists, like Roger Penrose, argue that consciousness itself might represent a fundamental aspect of physical reality not captured by current mathematical frameworks. A theory of everything might necessarily remain incomplete if it cannot integrate subjective experience with objective physical description. The multiverse interpretation of quantum mechanics offers another perspective. If multiple parallel universes exist with potentially different fundamental constants, a theory explaining our universe might be inherently limited in its explanatory power. Experimental limitations further complicate our quest. We can only observe a tiny fraction of the universe. Most of cosmic history and distant regions remain inaccessible. Any theory of everything would necessarily incorporate assumptions about unobservable regions, creating inherent uncertainties. Gödel's insight becomes particularly profound here. Just as mathematical systems contain statements that cannot be proven within their own framework, a physical theory might contain fundamental truths that can only be understood from a perspective outside the theory itself. The beauty of an incomplete theory of everything lies in its potential. It would represent not a final destination, but a profound invitation, a framework that simultaneously explains and points toward deeper mysteries. Science progresses not by achieving absolute truth, but by continually expanding the boundaries of our understanding. Ultimately, an incomplete theory of everything would be the most honest scientific achievement imaginable, a humble acknowledgement that reality is far more complex and mysterious than our most elegant mathematical descriptions can fully capture. Instantaneous velocity reversal. Imagine an object moving at a constant velocity, suddenly reversing its direction instantaneously, without slowing down, without passing through zero velocity, without any intermediate state. This seemingly simple scenario reveals profound challenges to our fundamental understanding of motion, acceleration, and the very nature of physical change. In classical mechanics, velocity is a vector quantity. It has both magnitude and direction. A typical object changing direction requires a finite time to decelerate, reach zero velocity, and then accelerate in the opposite direction. But our impossible scenario asks, what if this transition happens instantaneously, with no intermediate states? Consider the mathematical implications. Velocity is defined as the rate of change of position with respect to time. An instantaneous reversal would require infinite acceleration. A change in velocity occurring in zero time. This immediately triggers a cascade of physical impossibilities. Newton's second law states that force equals mass multiplied by acceleration. For an object to reverse velocity instantaneously, it would require an infinite force. An infinite force would imply infinite energy, infinite momentum, and would violate fundamental conservation laws that are bedrock principles of physics. Einstein's special relativity introduces additional complications. As an object approaches the speed of light, its relativistic mass increases. An instantaneous velocity reversal would require infinite energy to overcome this increasing mass, making the maneuver physically impossible even before considering the instantaneous nature of the change. Quantum mechanics offers another perspective. The uncertainty principle suggests that an object's position and momentum cannot be precisely defined simultaneously. An instantaneous velocity reversal would require perfect knowledge of both position and momentum at the exact moment of reversal, a direct violation of quantum mechanical principles. From an energy perspective, the instantaneous reversal would require an infinite energy transfer. Kinetic energy is calculated as 1/2 multiplied by mass multiplied by the square of velocity. An instantaneous reversal would imply an infinite energy state during the transition. No physical system can sustain or generate such infinite energy. Consider the mechanical stress on the object itself. An instantaneous reversal would subject every particle to infinite acceleration simultaneously. This would require infinite internal forces, instantly breaking every molecular bond. The object would essentially be destroyed at the moment of reversal, becoming a cloud of dispersed particles. Momentum conservation provides another barrier. For an object to reverse velocity instantaneously, it would need to transfer infinite momentum in zero time. This violates the fundamental principle that momentum must be conserved in any closed system. Even electromagnetic interactions pose challenges. At the atomic level, an instantaneous velocity reversal would require instantaneous reversal of electron motions, magnetic moments, and quantum spin states, all of which are fundamentally time-dependent processes. Some theoretical approaches suggest exploring this problem through thought experiments. What if we consider increasingly rapid velocity reversals, approaching but never reaching instantaneous change? Each approximation reveals the increasingly extreme energy and force requirements. Imagine throwing a ball. As it approaches instantaneous reversal, the forces required become progressively more extreme. The ball would compress, deform, heat up, and ultimately disintegrate long before achieving an instantaneous direction change. Real materials always have finite response times to applied forces. The problem connects to deeper philosophical questions about the nature of change. Aristotle argued that all change must be gradual, occurring through intermediate states. Our instantaneous reversal scenario directly challenges this fundamental understanding of physical transformation. What makes this impossible problem fascinating is how it reveals the deep interconnectedness of physical laws. Velocity reversal is not just about motion. It touches on energy conservation, quantum uncertainty, relativistic mass, momentum transfer, and the very nature of physical change. Ultimately, an instantaneous velocity reversal remains impossible. The universe maintains its fundamental constraints: finite energy transfer, conservation laws, quantum uncertainty, and the finite speed of information propagation. Physics allows us to imagine impossible scenarios, but reality always imposes its elegant, immutable limitations.